somewhere above us, beyond the soft glow of city lights, and far past the edge of our own galaxy, there is another vast island of stars, slowly moving in our direction. It has been moving this way for a very long time. If you step outside on a dark night, far from buildings and streetlights, you can actually see it. It appears as a faint, misty smudge in the sky. Most people would think it is just a blurry patch of light, but that small blur is an entire galaxy. It is called Andromeda Galaxy, and it is coming toward us. Now, that might sound dramatic, a whole galaxy moving closer. But don't worry, this is a very slow story, the kind that unfolds over billions of years, the kind that moves so gently that no one alive today will ever see even the smallest change. Still, the idea is fascinating. How do we even know it is moving toward us? After all, galaxies are so far away that even light from Andromeda takes about 2.5 million years to reach Earth. That means when you look at it tonight, you are seeing it as it was when early humans were just beginning to use stone tools. So how can we measure its motion? The answer begins with light. In the early 1900s, astronomers were studying distant objects in the sky using a tool called a spectroscope. This device spreads light out into a rainbow, much like a prism does. But instead of just showing colors, it reveals thin, dark lines within the light. These lines act like fingerprints. They tell us what elements are present and how they are moving. Here's where it gets interesting. When something moves away from us, its light stretches slightly. The colors shift toward the red end of the spectrum. This is called redshift. Imagine the sound of an ambulance siren as it drives away. The pitch drops lower. Light does something similar. And when something moves toward us, the opposite happens. The light shifts slightly toward blue. The waves get squeezed together. Like a siren coming closer, the pitch rises. This is known as blue shift. When astronomers studied the light from Andromeda, they noticed something surprising. The spectral lines were shifted toward blue, not red. That meant Andromeda was not drifting away like most galaxies. It was moving toward us at about 110 kilometers per second. Now, 110 kilometers per second might be hard to picture, so let's slow it down into something more familiar. 1 second. That's about the time it takes to snap your fingers. In that tiny moment, Andromeda moves 110 kilometers closer. That's about the distance from one side of a large city to another. Or imagine driving from one town to the next. That's how far it moves in a single second. In 1 hour, it would cover nearly 400,000 kilometers. That's about the same distance between Earth and the Moon. But even at that speed, the distance between us is so enormous that the collision won't happen for billions of years. So who first realized this? In the early 20th century, astronomers like Vesto Slipher were carefully measuring the light from spiral nebulae, as they were called at the time. Back then, people weren't even sure if Andromeda was inside our galaxy or something much farther away. Using careful measurements, Slipher noticed the blue shift in Andromeda's light. It was one of the first strong clues that the universe was not static. Things were moving. In fact, most galaxies were moving away from us, which later helped scientists understand that the universe itself is expanding. But Andromeda was different. It was one of the rare exceptions. A giant galaxy heading our way. Why would that happen when everything else is moving apart? The answer lies in gravity. While the universe is expanding overall, gravity still pulls nearby objects together. And Andromeda is not just nearby. On a cosmic scale, it's practically our neighbor. It is about 2.5 million light years away. That sounds far, and it is. If you could travel at the speed of light, which is about 300,000 kilometers per second, fast enough to circle Earth 7 times in 1 second, it would still take you 2.5 million years to get there. But in galactic terms, that's close enough for gravity to matter. Our galaxy, the Milky Way, and Andromeda, are the two largest members of a small group of galaxies called the Local Group. This group is like a quiet neighborhood in space, containing around 50 smaller galaxies, along with the two giants. The Milky Way and Andromeda are the heavyweights of this neighborhood. Each contains hundreds of billions of stars, and gravity between them acts like a slow, steady pull, like two massive whirlpools in a vast ocean, slowly drifting toward each other. You might wonder, has Andromeda always been moving toward us? Not exactly. Billions of years ago, shortly after the universe began expanding, galaxies were carried outward with that expansion. But over time, gravity between nearby galaxies began to compete with that expansion. In our local neighborhood, gravity won, and so the two largest galaxies began falling toward each other, not in a straight line like two cars on a highway, but in a complex, slow dance, shaped by invisible forces. Invisible forces, yes, because what we see, the glowing stars, is only a small part of the story. Both galaxies are surrounded by enormous halos of dark matter. We can't see dark matter directly, but we know it is there because of how galaxies move. These halos are far larger than the visible disks of stars. If the bright part of the Milky Way is like a glowing dinner plate, the dark matter halo would be like an invisible cloud many times wider than the plate. And these halos are already interacting. Even now, right now, as you sit or lie there listening, gravity is gently pulling these two vast systems closer together, not with any sudden motion, not with drama, just a steady drift that has been happening for billions of years. And it will continue. The idea can feel strange. Our galaxy feels permanent, solid, like it has always been here, and always will be. But nothing in the universe stands still. Everything moves. Everything changes. Even entire galaxies. And far above us, that faint blur in the night sky, that soft oval of light, is not just sitting quietly. It is on a long journey toward us. A journey measured not in days or centuries, but in spans of time so large they are hard to grasp. Yet we know it is happening. Because light, traveling across millions of years, carries the message. And that message says, we are not alone in this part of space. Something enormous is coming closer, very slowly, very gently, and the story of what will happen next stretches far into the deep future. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. If Andromeda is slowly moving toward us, a natural question begins to form. How big is it? Is it similar to our galaxy, or something much larger? When we look at the Milky Way from inside, it feels endless. On a clear night, that pale band of light stretching across the sky is just a thin slice of its disk. But from edge to edge, our galaxy spans about 100,000 light-years across. That number can feel abstract, so let's shrink it down in our imagination. If the Milky Way were the size of the continental United States, stretching from one coast to the other, our entire solar system would be smaller than a coin placed on one city block. The Sun, Earth, and all the planets would barely register on that map. That is how vast our galaxy is. Now, what about Andromeda? The Andromeda galaxy is even larger. Current estimates suggest it stretches roughly 220,000 light-years across. That means if the Milky Way is like a large dinner plate, Andromeda would be more like a serving platter, almost twice as wide. Imagine two giant spinning disks made of hundreds of billions of stars. One is large, the other is larger still. And what about the number of stars? The Milky Way is thought to contain somewhere between 100 and 400 billion stars. That's already difficult to picture. If you tried to count one star every second without ever stopping, no sleep, no breaks, it would take you thousands of years just to reach 1 billion. Now multiply that by hundreds. Andromeda may hold close to 1 trillion stars. That's 1,000 billion. If each star were a grain of sand, you would need enough sand to fill a massive beach, stretching farther than you could see in both directions. So yes, in terms of sheer star count and physical size, Andromeda appears to be the larger of the two. But size is not just about width. It is also about mass. Mass includes stars, gas, dust, and something far more mysterious: dark matter. When astronomers measure how fast stars move around the centers of galaxies, they notice something strange. The stars move much faster than they should, if only visible matter were present. It's like watching leaves spin around a whirlpool much faster than the water you can see would allow. This tells us there must be extra mass, invisible mass, holding everything together. Both galaxies are surrounded by enormous halos of dark matter. If the visible disk of stars is like the bright flame of a candle, the dark matter halo would be like an invisible sphere many times larger, extending far beyond the glow. For Andromeda, that halo may stretch well over 1 million light-years across. That's 10 times wider than the visible part of the Milky Way. If the bright disk were the size of a city, the dark matter halo would extend far beyond the entire country. So which galaxy is heavier overall? For a long time, scientists thought Andromeda was clearly more massive. But newer measurements suggest the two may be closer in mass than we once believed. It's possible they are like two heavyweights in the same weight class. One slightly taller perhaps, but similar in overall strength. This raises another gentle question. If Andromeda is larger, does that mean it will win when the two galaxies meet? The answer is not quite that simple. Galaxies are not solid objects, like rocks colliding. They are more like vast swarms of bees. Each star is separated from its neighbors by enormous distances. If the Sun were the size of a marble, the nearest star would be another marble, placed thousands of kilometers away. That means when the two galaxies eventually pass through each other, most stars will simply glide by without touching. But the overall shape will change. You can imagine two large clouds of fireflies drifting toward each other. Each firefly moves mostly through empty space, but gravity gently reshapes the whole swarm. That is what will happen. Andromeda's spiral arms are already visible through telescopes. They wind outward in elegant curves, filled with young blue stars and glowing pink clouds of gas. The Milky Way has similar arms, though we see them from the inside. So in many ways, the two galaxies are like siblings. Similar structure, similar shape, similar ingredients. Two grand spiral galaxies, each rotating slowly, each taking hundreds of millions of years just to complete one full turn. If Earth's entire history, all 4.5 billion years, were compressed into a single day, one rotation of the Milky Way would still take about 2 hours on that clock. That's how slowly galaxies spin. And yet, even with all that slowness, gravity has been working quietly between them. You might wonder, if Andromeda is bigger, does that mean we are small in comparison? Not really. On the scale of the universe, both galaxies are giants. There are smaller dwarf galaxies, with only a few billion stars, tiny compared to our home, and there are even larger galaxies in distant clusters that stretch far wider than either of ours. But within our local group, these two dominate. They account for most of the mass, most of the stars, most of the structure. They are the central pair in this quiet region of space. And slowly, steadily, they are closing the distance. Right now, they are separated by about 2.5 million light-years. If that distance was scaled down so that the Milky Way and Andromeda were two coins placed on a table, they would still be several meters apart, almost across the room, close enough to see each other clearly, but far from touching. Over time, that space will shrink. Not suddenly, not violently, just gradually. And when they finally begin to overlap, it will not be two solid walls crashing together. It will be two enormous, graceful systems of stars, gas and dark matter slowly blending. But before that happens, we must think about time. How long will it take? Is this something happening soon in cosmic terms, or far beyond anything we can truly imagine? That quiet question leads us deeper into the future, billions of years ahead, where the timeline of this slow approach becomes even more astonishing. If Andromeda is moving toward us at about 110 kilometers every second, covering a distance equal to traveling across a large city in the time it takes to snap your fingers, the next natural question feels almost automatic. When will it finally arrive? The answer stretches far beyond everyday time. Astronomers estimate that the first close encounter between the Andromeda galaxy and the Milky Way will happen in about 4 to 5 billion years. 4 to 5 billion. That number can feel distant, almost unreal. So let's try to make it more familiar. The Earth itself is about 4.5 billion years old. That means the time between now and the collision is roughly equal to the entire age of our planet so far. Imagine replaying Earth's whole story again, from molten lava oceans to the first tiny cells in the sea, to dinosaurs, to humans. And only then would Andromeda begin its first major pass. That's how far into the future we're talking about. In human terms, it's unimaginably long. If one human lifetime is like a single breath, then 5 billion years is like holding that breath for longer than the history of every civilization combined, multiplied again and again. So no, this is not something looming over us tomorrow. But here's something interesting. That timeline, 4 to 5 billion years, lines up closely with another major event in our cosmic future. Our Sun. The Sun is currently about 4.6 billion years old. It's middle-aged, in a way. Stars like the Sun live for roughly 10 billion years before they begin to change dramatically. In about 5 billion years, the Sun will start running low on hydrogen fuel in its core. When that happens, it will begin to swell outward. It will become what astronomers call a red giant. What does that mean? Right now, the Sun is about 1.4 million kilometers wide. That's wide enough to fit more than 100 Earths side by side across its surface. But when it expands into a red giant, it may grow large enough to swallow Mercury, possibly even Venus, maybe Earth. If the Sun were the size of a basketball today, its red giant version would expand to the size of a small room. So around the same era, when galaxies begin their slow dance toward merging, our own star will be entering its final dramatic phase. You might wonder, which happens first, the galaxy collision or the Sun's transformation? They overlap. The first close pass between Andromeda and the Milky Way is expected around 4 billion years from now. The Sun's red giant phase begins roughly around 5 billion years from now. So as galaxies stretch and reshape each other across millions of light years, our own solar system may already be dealing with changes much closer to home. But let's return to the galactic timeline. When scientists say collision in 4 to 5 billion years, what do they really mean? It's not like two cars smashing at a precise second. Instead, the process unfolds slowly. First, the galaxies approach, then they pass through each other. Then gravity pulls them back together again. They may separate briefly before falling inward once more. Over perhaps 1 to 2 billion additional years after the first encounter, they gradually merge into a single new galaxy. So from first contact to final union, the whole event may last 2 billion years or more. If 1 year is like 1 second on a clock, that merger would last longer than an entire human civilization multiplied millions of times over. And yet, in cosmic terms, it's just another chapter. You might ask, how certain are we about this timeline? After all, predicting events billions of years into the future sounds bold. Astronomers use detailed computer simulations, They measure Andromeda's speed, direction, and distance. They observe how gravity works across vast systems. Then they run models, like advanced cosmic weather forecasts, projecting how these massive galaxies will move under gravity's pull. Of course, small uncertainties remain. Andromeda also has sideways motion, not just motion toward us. That sideways component affects how directly the galaxies will meet. But the overall result remains clear. They are bound together by gravity, and unless something extremely unusual happens, they will merge. There is no sign of escape. In fact, their mutual gravity is already overcoming the overall expansion of the universe in our local region. On very large scales, galaxies drift apart as space itself stretches. But locally, gravity holds clusters together. It's like dots drawn on a stretching rubber sheet. Most dots drift apart as the sheet expands. But if two dots are connected by a strong spring, they can still move toward each other. The Milky Way and Andromeda are connected by that gravitational spring, and it has been tightening for billions of years. Sometimes people hear galaxy collision and imagine something sudden and destructive. But remember, space inside galaxies is mostly empty. The average distance between stars is enormous. If the sun were the size of a grape, the nearest star would be another grape located thousands of kilometers away. That means even when galaxies overlap, most stars simply pass by one another. The real changes happen slowly, through gravity's steady pull. So when will it happen? Not in our lifetime, not in the lifetime of our species, not even in the lifetime of the Earth as we know it today. It belongs to a future so distant that continents will have shifted beyond recognition. Oceans may have changed shape. The sun itself will be evolving. And yet, the motion has already begun. Right now, in this quiet moment, Andromeda is moving closer. Every second, that distance shrinks by about 110 kilometers, roughly the length of a long highway drive. Over 1 year, that adds up to about 3.5 billion kilometers. That's more than 20 times the distance between Earth and the Sun. It doesn't feel like movement. The night sky looks steady and calm, but deep time is patient, and gravity never sleeps. The meeting is set. It just requires a scale of time far larger than anything we experience. And when that time finally arrives, the meaning of the word collision will turn out to be something far gentler and far stranger than it sounds. When people hear the words galaxy collision, the image that often comes to mind is dramatic. Two massive star systems crashing together, like two planets smashing head-on. Explosions everywhere. Stars slamming into each other, fire filling the sky. But that image is not quite right. In reality, a galaxy is not a solid object. It is not like a rock or a planet. It is mostly empty space. Very, very empty. Let's slow down and picture this. Our sun is about 1.4 million kilometers wide. That's wide enough to fit more than 100 Earths side by side across its face. It feels huge. Now imagine shrinking the sun down to the size of a small marble. On that scale, how far away would the nearest star be? Not a few meters away. Not even in the same city. It would be thousands of kilometers away, about the distance from one country to another. That's how spread out stars are inside a galaxy. So, when two galaxies pass through each other, it's less like two rocks colliding, and more like two enormous swarms of fireflies drifting through one another in the dark. Each firefly keeps flying. They rarely bump into each other, but the swarm as a whole changes shape. That is what a galaxy collision really is. The word collision sounds violent, but in space it's more of a slow blending. Even though the Milky Way contains hundreds of billions of stars, and the Andromeda galaxy may contain close to 1 trillion, the chances of two individual stars directly hitting each other are extremely small, almost zero. You might wonder, How can that be possible with so many stars? The answer is space itself. Space is wide beyond intuition. If stars were grains of sand, the gaps between them would be miles wide. Even when two entire galaxies overlap, most stars simply glide past one another without touching. So what actually interacts? Gravity. When galaxies approach, their gravitational fields begin to pull and stretch each other. It's like two slow-moving whirlpools in a vast ocean. As they come close, their shapes distort. Long streams of stars can be pulled outward, forming what astronomers call tidal tails. These tidal tails can stretch hundreds of thousands of light years. If 1 light year is about 9.5 trillion kilometers, a distance so large that even light takes a full year to cross it, then a tidal tail can extend for hundreds of thousands of those distances. If you scaled a galaxy down to the size of a dinner plate, a tidal tail would stretch far across the entire room. So the collision is not about impact, it's about reshaping. There's another important part of this story: gas and dust. While stars are far apart, clouds of gas inside galaxies are much more spread out. These clouds are the raw material for new stars. And when galaxies pass through each other, these gas clouds can collide and compress. When gas gets compressed, it can trigger bursts of new star formation. Imagine squeezing a soft sponge filled with water. The pressure forces things together. In space, that pressure can cause gravity to pull gas inward until it ignites into new stars. So rather than destruction, galaxy collisions often create new stars. In fact, some of the most beautiful galaxies we see in the universe today, glowing, twisted, full of bright young stars, are galaxies in the middle of merging. So, if stars rarely hit each other, is there any danger at all? There can be changes. Even without direct collisions, gravitational forces can alter the paths of stars. The orbits of entire solar systems can shift. A star that once circled peacefully in one part of the galaxy might end up in a completely different region. But these changes happen over millions of years, not overnight. You might ask, if galaxies are mostly empty, why do they look so bright and solid in pictures? That's because when we look at a galaxy, we see billions of stars blended together. From far away, the combined light creates a glowing disk or spiral. But zoom in close enough, and you would find vast stretches of darkness between each star. If you could stand near a star in another galaxy, during the merger, you likely wouldn't even notice nearby stars passing by. The sky might slowly change shape over millions of years, but there would be no sudden flashes or impacts. It's almost peaceful in its own way. The word collision makes it sound quick, but this process unfolds over billions of years. That's longer than Earth has existed so far. If Earth's entire history were one 24-hour day, the actual moment of galactic overlap would last hours and hours on that clock, a slow-motion dance. So why do scientists still use the word collision? Because from a gravitational point of view, these systems do interact strongly. They exchange energy, they merge into one structure. Their original shapes are lost. Two separate spirals eventually become one new galaxy. But not through smashing, through blending, through gravity patiently pulling and reshaping. And perhaps that is the most surprising part. When you imagine the future meeting between the Milky Way and Andromeda, you might expect chaos. Instead, it will be something vast and slow, stars drifting, gas compressing, gravity weaving two systems together, and all of it happening so gradually that from the perspective of any single star, the universe would still feel calm. It is a reminder that even the largest events in the cosmos are not always violent in the way we imagine. They are immense, they are transformative, but they are also quiet. And before the bright disks of stars ever begin to overlap, something even larger, something invisible, will meet first. Long before the glowing spirals touch, Their hidden halos will begin interacting in the dark, long before the bright spiral arms of the Milky Way and the Andromeda galaxy ever appear to touch. Something much larger will meet first. Not the stars, not the glowing gas, something invisible. Both galaxies are surrounded by enormous halos of dark matter. We cannot see dark matter. It does not shine, reflect, or absorb light, but we know it is there because of how galaxies move. Think of it like the wind. You can't see the wind itself, but when trees bend and leaves move, you know something unseen is pushing them. Dark matter is like that invisible wind, except instead of pushing leaves, it shapes entire galaxies. The visible part of the Milky Way, the glowing disk with its spiral arms, stretches about 100,000 light-years across, but its dark matter halo extends far beyond that, possibly more than 1,000,000 light-years wide. If the bright disk were the size of a dinner plate, the dark halo would be like an enormous invisible bubble surrounding the entire house. And Andromeda has one too. So before the stars come close, these giant invisible halos will begin to overlap. You might wonder, what does that even mean? Since dark matter doesn't bump into itself the way gas does, the overlap is not like two clouds colliding. It's more subtle. It's about gravity. Each halo carries enormous mass. In fact, most of a galaxy's mass may be in its dark matter halo. That means when the halos begin to overlap, their gravitational pull starts to change the motion of both galaxies. Imagine two huge whirlpools in a calm ocean. From far away, the water seems still, but as the whirlpools drift closer, the currents begin to feel each other. The surface slowly changes. That is the first true encounter, and this will happen long before the stars visibly mix. Right now, the distance between the two galaxies is about 2.5 million light-years. That's a number so large it's hard to hold in your mind. If 1 light-year were the length of a football field, then 2.5 million light-years would stretch farther than the distance around the entire Earth, many times over. But because the halos are so wide, their outer edges may already be feeling each other's gravity in subtle ways. Over the next billion years, that influence will grow stronger. The galaxies will begin to accelerate slightly toward each other, not in a sudden rush, more like a gentle downhill roll that slowly gains speed. Gravity does not need contact to work. It reaches across space. You might ask, if this is happening so gradually, would anyone inside the galaxy notice? The answer is probably not, at least not at first. Stars orbit the center of their galaxy at speeds of hundreds of kilometers per second. Our own sun moves around the center of the Milky Way at about 220 kilometers per second. That's fast enough to travel from one major city to another in just a second. Yet even at that speed, it takes the sun about 230 million years to complete one full orbit around the galaxy. That's one galactic year. So when the halos begin interacting, the changes will be extremely slow compared to a single star's motion. The overall gravitational balance will shift bit by bit, like adjusting the weight distribution on a slowly spinning carousel. Over time, as the halos overlap more deeply, the gravitational pull between the two galaxies will grow stronger. This will set the stage for their first close pass. It's almost like two dancers stepping closer on a dark stage. Before their hands touch, before their bodies move together, there is a shift in posture. A shared pull, a recognition the invisible parts meet first. And because dark matter makes up most of the mass, this stage is incredibly important. The way the halos interact will influence the shape of the eventual merger. You might wonder something else. If dark matter is invisible and doesn't collide like normal matter, why does it matter so much? Because gravity depends on mass, and dark matter provides most of the mass. Without dark matter halos, galaxies might not even exist in their current form. Stars would not orbit the way they do. Spiral structures might not hold together. So when the halos overlap, it's like the foundations of two cities beginning to merge before the buildings ever touch. This early gravitational encounter will stretch the outer regions of both galaxies. Some stars on the edges may begin to feel a slight tug, altering their paths ever so slightly. It won't look dramatic at first. There won't be fireworks in the sky. The night view from a planet inside the Milky Way would still look mostly familiar. But over millions and millions of years, the influence will build, the approach will accelerate, and eventually, the visible disks of stars will begin to distort. That distortion, the bending and stretching of spiral arms, will be the next visible sign of this slow cosmic meeting. But it all begins here, with invisible halos, with gravity reaching across millions of light years, with two vast systems, each containing hundreds of billions of stars, beginning to feel each other's presence in the quiet dark. Long before contact, long before light meets light, the encounter has already begun. Before the bright spiral arms ever stretch toward each other, before gas clouds collide, before new stars begin to form in bursts of light, the real meeting happens in silence. It happens in the dark. Both the Milky Way and the Andromeda galaxy are wrapped in enormous halos of dark matter. These halos are not thin shells. They are vast, round regions that extend far beyond the glowing disks we see in pictures. If the visible part of each galaxy were like a bright coin, the dark matter halo would be like a giant invisible balloon surrounding it, many times wider than the coin itself. The Milky Way's bright disk is about 100,000 light-years across, but its halo may stretch over 1,000,000 light-years. That's 10 times wider. If the bright disk were the size of a small plate on a table, the halo would be large enough to cover the entire house. And Andromeda's halo is just as enormous. So when we imagine the two galaxies approaching each other, we shouldn't picture two thin spirals slowly drifting closer. We should picture two massive invisible spheres already overlapping long before the stars appear to touch. You might ask, what does it mean for halos to overlap? Dark matter does not behave like gas or dust. It doesn't crash or heat up. It doesn't glow. It simply moves under gravity. When the halos begin to overlap, it means their gravitational fields begin mixing more strongly. The total pull between the galaxies increases. Each galaxy begins to feel the other, not just as a distant object, but as a growing presence shaping its structure. Imagine two hills made of sand, far apart at first. Each hill has its own slope, but as you slowly push them closer, the edges of their slopes begin to blend. The shape of each hill changes even before the peaks meet. That blending of slopes is similar to what happens with dark matter halos. The gravitational landscape around each galaxy begins to shift. Stars in the outer edges of both galaxies will feel this change first. Their orbits may stretch slightly. Some may drift farther out. Others may begin to fall inward. The changes are small at first, almost impossible to notice on short timescales, but over millions of years, the effects add up. Right now, the two galaxies are about 2.5 million light-years apart. If 1 light-year were the length of a single step, that would be 2.5 million steps, like walking across entire countries. But since the halos stretch so far, their outer regions may already be interacting at the edges. This stage is quiet. There are no bright flashes, no dramatic visuals, but gravity is patient. It reshapes things slowly. You might wonder, does this overlap slow them down or speed them up? It does both, in a way. As the galaxies fall toward each other, gravity pulls them inward, increasing their speed. But at the same time, their dark matter halos begin to mix and exchange energy in a process called dynamical friction. That phrase might sound complex, but the idea is simple. Imagine pushing your hand through water. The water resists slightly. It slows your hand down. In space, when a massive object moves through a field of particles, even invisible dark matter particles, it creates a wake behind it. That wake pulls backwards slightly, acting like a gentle break. This braking effect causes the galaxies to lose orbital energy over time, making it harder for them to simply swing past each other and escape. Instead, they become more tightly bound. It's like two ice skaters gliding toward each other. If they barely touch hands and push off, they might separate again, but if there's friction between them, they lose energy and remain connected. The overlap of dark matter halos ensures that when the Milky Way and Andromeda finally make their first close pass, they won't simply drift apart forever. They are destined to merge. This invisible stage sets the outcome. Without dark matter halos, the encounter might look very different. The galaxies might pass by and continue on separate paths, but because of these massive halos, gravity holds them in a long, slow embrace. You might ask, how do we know dark matter halos are this large? Astronomers measure how stars move at different distances from the center of galaxies. Surprisingly, stars far from the center move almost as fast as those closer in. If only visible matter were present, stars at the edges should move much slower, like planets farther from the sun orbiting more slowly. But they don't. This tells us there must be extra mass extending far beyond the bright disk. That extra mass forms the halo. So, as the halos overlap more deeply over the next billion years, the entire structure of both galaxies will begin to feel unstable in subtle ways. The spiral arms will not immediately twist or break, but the foundation beneath them, the gravitational support, will start shifting. It's a bit like adjusting the foundation of a large building. From outside, the walls still stand tall, but over time, small cracks appear. Angles change, the shape evolves. The halo overlap is the beginning of that transformation. Invisible, silent, but powerful. Long before stars stream into long arcs, long before bright new clusters light up the sky, long before black holes spiral together, the real encounter begins in the dark. Two enormous spheres of unseen matter slowly blending across millions of light years. A meeting you would never see with your eyes, but one that changes everything that follows. As the invisible halos continue to overlap and gravity pulls more strongly between the two galaxies, something new begins to happen. The shapes start to change. Not suddenly, not violently, but gradually, like soft clay being gently stretched by unseen hands. The Milky Way and the Andromeda galaxy are both spiral galaxies. Each has a bright central bulge and long curved arms wrapping outward like a spinning pinwheel. Right now, those arms are fairly stable. Stars move along them in steady orbits, taking hundreds of millions of years to complete one circle around the galactic center. But as the galaxies draw closer, gravity does not pull evenly on every part. The side of each galaxy facing the other feels a slightly stronger pull than the far side. That uneven tug creates what astronomers call tidal forces. You've seen tidal forces before. Here on Earth, the moon pulls on our planet's oceans. The side of Earth facing the moon feels a slightly stronger pull than the center, and the far side feels a slightly weaker pull. This difference creates ocean tides. Now imagine tides, not in water, but in stars. Instead of oceans rising and falling by a few meters, entire sections of galaxies begin to stretch across tens of thousands of light years. If one light year were the length of a football field, then 10,000 light years would stretch far beyond the horizon, farther than you could ever see, and tidal forces can stretch material even farther than that. As the galaxies approach their first close pass, about 4 billion years from now, these tidal forces grow much stronger. The spiral arms begin to elongate. Stars at the edges are pulled outward into long streams. These streams are called tidal tails. They can extend hundreds of thousands of light years into space, like glowing ribbons trailing behind the galaxies. If the Milky Way were the size of a large plate, these tidal tails would stretch across the entire room and out the door. You might wonder, Do the stars in those tails get flung away forever? Some do. A few stars may gain enough speed from the gravitational interaction to escape entirely, drifting into intergalactic space, but most remain loosely bound, eventually falling back into the merging system. From a distance, the scene would look breathtaking. Two grand spirals, once neatly shaped, now twisting and warping as gravity pulls them into strange new forms. Their arms no longer symmetrical, their centers shifting. But remember, this happens over millions of years. If you were living on a planet during this time, the changes would be slow, almost unnoticeable from one generation to the next. Yet over long spans, the night sky would begin to look different. You might see a bright arc of stars stretching across a region where darkness once was. You might notice Andromeda, once a small smudge, now appearing larger, more detailed, filling more of the sky. Why does gravity stretch instead of simply pulling everything straight inward? Because galaxies are rotating. Stars are already moving sideways as they orbit the center. When an external gravitational pull acts on them, it doesn't just drag them inward, it changes their paths, stretching them into curved streams. Imagine two spinning plates of glitter sliding past each other. As they pass, some glitter gets pulled outward in streaks rather than simply falling inward. That's tidal distortion. The centers of the galaxies will likely survive the first close pass, but the outer regions will be heavily reshaped. In fact, computer simulations show that during the first encounter, the galaxies may pass through each other and then swing apart again. The tidal forces during that pass are strong enough to create dramatic distortions, but not yet enough to fully merge them. It's like two dancers rushing past each other, arms extended, grabbing and pulling fabric as they spin by, and that pulling sets the stage for what comes next. You might ask, how close will they get during the first pass? Estimates suggest their centers could come within perhaps 100,000 light-years of each other. That's roughly the width of the Milky Way itself. On a cosmic scale, that's incredibly close. If two dinner plates were that close on a table, their edges would nearly overlap. During this time, the gravitational pull will stir up gas clouds inside both galaxies. Those clouds will begin colliding and compressing, preparing for bursts of new star formation. But before that bright activity begins, the distortion itself is the first visible sign of deep interaction. The elegant spiral patterns will no longer look stable. Arms may appear stretched and torn. The symmetry we associate with spiral galaxies will fade, and something else begins to happen quietly at the center. As the galaxies distort, their central regions, containing supermassive black holes, are slowly drawn toward each other. But that story unfolds later. For now, we remain in this stage of stretching, of reshaping, of gravity pulling stars into long, graceful arcs. It is not chaos in the explosive sense. It is a slow transformation, a reminder that even structures spanning hundreds of thousands of light-years can bend under gravity's patient hand. And as those tidal tails grow longer and brighter, the night sky in the far future would become something almost unimaginable. Not empty, not still, but alive with vast, luminous streams of stars, tracing the path of two galaxies caught in each other's pull. As the two galaxies stretch and twist under tidal forces, something remarkable begins to happen deep inside their clouds of gas. New stars are born, not just a few here and there, but in great numbers. Right now, in the Milky Way, about 1 or 2 new stars form each year. That may sound like a lot, but in a galaxy with hundreds of billions of stars, it's actually a slow and steady pace. Think of it like planting 1 or 2 new trees each year in a forest that already has billions. The forest grows, but gently. During a galactic encounter, that pace can change dramatically. When the Andromeda galaxy makes its first close pass, huge clouds of gas inside both galaxies will collide and compress. Unlike stars, gas clouds are not tiny points separated by enormous distances. They are vast and diffuse, but when galaxies overlap, these clouds can run into each other directly. And when gas is squeezed, gravity takes over. Imagine pressing your hands together on a soft pillow. The material inside bunches up and becomes denser. In space, when gas becomes dense enough, gravity pulls it inward. As it collapses, it heats up. Eventually, the core becomes so hot and so compressed that nuclear fusion begins. A new star ignites. During galaxy mergers, this process can happen on a much larger scale. Instead of 1 or 2 stars forming per year, the rate can rise to dozens, even hundreds per year. Astronomers call this a starburst. If normal star formation is like a quiet campfire, a starburst is like adding fresh logs and watching the flames leap higher. You might wonder, how long would this starburst last? Not forever. The intense phase might last a few 100 million years. That sounds long to us, but in galactic time, it's brief. If the entire 4 billion year collision process were a full day, the starburst would be just a few minutes within it. Still, those few minutes would fill the merging galaxies with brilliant new light. Many of these newborn stars would be massive and hot. Massive stars burn their fuel quickly. Some may live only a few million years, like candles that burn bright and fast. When they die, they explode as supernovae, scattering heavy elements into space. So the collision does not just create stars, it creates the materials for future planets. Carbon, oxygen, iron, the elements that make up rocks, oceans, even living things. You might ask, would this make the night sky brighter? Yes, very likely. As Andromeda grows larger in the sky during the approach, and as new stars ignite across both galaxies, the distant sky could glow more brightly than it ever has before. Instead of a faint mist, Andromeda might stretch across a large portion of the sky, showing detailed structure. Bright clusters of newborn stars could appear as glowing knots of light. If you imagine today's full moon, bright enough to cast shadows, the combined glow of merging galaxies could rival that brightness in some regions of the sky. Not all at once, but in patches. And yet, this burst of creation is temporary. As gas is used up in forming new stars, the supply gradually runs low. Star formation slows again. It's a bit like a rainstorm after humid air rises and cools. The storm pours intensely, but eventually the moisture is spent. There is another gentle question here. Does this increased star formation make the merger dangerous? Not in the way people often imagine. While more massive stars mean more supernovae, space is so vast that the chance of one exploding close enough to affect a particular planet remains small. The danger is not zero, but it's not widespread destruction either. Most of the galaxy would remain peaceful, even during a starburst. From a distance, the merging system would look stunning, bright, chaotic, glowing with new life. Many of the most beautiful galaxies astronomers observe in the distant universe are caught in this stage. Twisted shapes, filled with young blue stars. In fact, when we look deep into space with powerful telescopes, we often see galaxies in the middle of merging. They remind us that this process is not rare. It is part of how galaxies grow. So in a way, the future collision between the Milky Way and Andromeda is not unusual. It is a continuation of cosmic evolution. Stars form, stars die, galaxies interact, new structures arise. The starburst phase is one of the most energetic chapters in that story. For a time, the merging galaxies will shine brighter than before. Regions that were once calm will blaze with new light. Vast clusters containing thousands of young stars may form together, bound tightly by gravity. If one of those clusters were placed near us today, it would outshine many of the stars in our night sky. And yet, through all of this brightness and activity, individual stars, like our Sun, would continue their own quiet journeys around the galactic center. The collision is grand. The creation is widespread. But life around a stable star could continue largely undisturbed. And that leads to a deeply personal question. As new stars are born in great numbers across the merging galaxies, what happens to our own star? Where will the Sun be during all of this? Will it drift into a new region of space, or remain where it is? The answer lies in the path our solar system will take through this slow and unfolding cosmic dance. As galaxies twist, stretch, and ignite with new stars, it's natural to turn the question inward. What happens to us? Not just to Earth, but to our entire solar system. Right now, our Sun quietly orbits the center of the Milky Way at about 220 kilometers per second. That's fast enough to travel from one major city to another in the time it takes to blink. Yet, because the galaxy is so enormous, it still takes the Sun about 230 million years to complete one full orbit. That means, since dinosaurs first appeared, the Sun hasn't even completed a full circle around the galaxy once. We are passengers on a very slow journey. When the Andromeda galaxy makes its first close approach, the Sun will still be orbiting as it always has, but the gravitational landscape around it will begin to change. You might wonder, will the Sun collide with another star? The simple answer is almost certainly no. Remember how far apart stars are. If the Sun were a marble, the nearest star would be another marble thousands of kilometers away. Even during a galactic merger, the chance of two stars directly hitting each other is extremely small. It's far more likely that stars simply pass by one another at great distances, so the Sun is unlikely to smash into anything. But that doesn't mean nothing changes. Gravity from Andromeda will disturb the overall structure of the Milky Way. As the galaxies pass through each other, stars will feel shifting gravitational pulls from different directions. Instead of moving in smooth circular paths around the galactic center, some stars will find their orbits stretched or tilted. Imagine running on a circular track, and suddenly the ground beneath you begins to shift slightly. You're still running, but the path is no longer perfectly round. It bends. It warps. The Sun's orbit could change in a similar way. It might move farther from the galactic center, or slightly closer. It could even be tossed into a new, more elongated path. Computer simulations suggest that there is a reasonable chance the Sun could be flung outward into the outer regions of the newly forming galaxy, not ejected into deep space, but moved far from the crowded center. How far? Possibly hundreds of thousands of light years from the core. If today the Sun is about 26,000 light years from the center of the Milky Way, roughly 1/4 of the way out from the center to the edge, then after the merger, it might find itself much farther out, perhaps near the outer halo of the new galaxy. If the galaxy were the size of a large city, it would be like moving from a busy downtown area to a quiet suburb at the edge. Would that be dangerous? Not necessarily. In fact, being farther from the crowded center might reduce the chances of close stellar encounters. You might ask, could another star pass near enough to disturb our planets? It's possible, but still unlikely. Even during a merger, the average distance between stars remains vast. A star passing close might still be trillions of kilometers away, that could gently tug at distant objects like comets in the outer solar system. But it probably wouldn't rip planets out of orbit. The inner solar system, where Earth, Mars, and the other planets orbit, would likely remain stable. However, the sky would change dramatically. As Andromeda grows larger over millions of years, it would fill more and more of the sky. Eventually, it could appear many times wider than the full moon looks today. Its bright core and spiral arms would become clearly visible. During the first close pass, the sky might be filled with sweeping arcs of stars from both galaxies. If you imagine looking up and seeing not just a thin band of the Milky Way, but enormous, luminous structures stretching from horizon to horizon. You begin to sense how different the view would become. And yet, on the ground, life, if it still exists, would not feel a sudden jolt. The changes are slow, so slow that even over thousands of years, the sky might only shift slightly. You might also wonder something deeper. What if the sun were ejected completely from the galaxy? Is that possible? In theory, yes. During the chaotic gravitational interactions of a merger, some stars can gain enough energy to escape entirely, becoming what astronomers call rogue stars. But simulations suggest the probability of the sun being completely ejected is small. More likely, it will remain bound to the newly formed galaxy, drifting in a new orbit, quietly circling a new center. There is something almost comforting in that thought. Even during the largest cosmic event our galaxy will ever experience, the Sun, and likely its planets, will continue their slow journey. Of course, there is one important detail. By the time the galaxies fully merge, the Sun itself will be nearing the end of its life. Around the same era as the collision, it will begin expanding into a red giant. So while the galaxy reshapes itself on a scale of hundreds of thousands of light years, the Sun will be undergoing its own transformation on a scale of millions of kilometers. Two immense changes unfolding at once, one vast and distant, one close and personal. The galaxy may twist and merge, the Sun may swell and brighten, but the solar system's fate during the merger is not one of violent destruction. It is one of movement, of shifting paths, of a new orbit within a newly formed galaxy. And that raises another quiet possibility. If gravitational forces can reshape orbits, could they go further? Could they ever fling an entire solar system out into the darkness between galaxies? That possibility, though rare, is worth gently exploring. When two galaxies begin their long, slow merge, gravity becomes the main actor. It pulls, it stretches, it reshapes, and sometimes it flings. So a quiet but fascinating question appears. Could our solar system be thrown completely out of the galaxy? Could Earth, along with the Sun, be sent drifting into the vast space between galaxies? The short answer is, it's possible, but it's not very likely. To understand how this could happen, we need to picture what occurs during close gravitational encounters. When the Milky Way and the Andromeda galaxy pass near each other, stars in both galaxies feel complex gravitational forces from many directions. Imagine standing in the middle of a crowd where everyone is gently pulling on each other with invisible ropes. Most of the time, the pulls balance out, but occasionally one person might get tugged strongly in one direction and stumble out of the group. In space, that stumble can become an escape. If a star passes near another massive object at the right angle and speed, it can gain extra energy from the interaction. This is called a gravitational slingshot. You've seen a version of this in space missions. Spacecraft use the gravity of planets to speed up. They swing around a planet and leave with more velocity than they had before. The same principle works with stars. If the Sun were to pass close enough to a massive star or dense region during the merger, it could, in theory, gain enough speed to escape the combined gravity of the new galaxy. But how much speed would that require? To escape a galaxy, a star needs to reach what is called escape velocity. For the Milky Way, that's roughly 500 to 600 kilometers per second near our region. Right now, the Sun moves around the galaxy at about 220 kilometers per second, so it would need more than double its current speed to break free completely. That's like driving at highway speed and suddenly needing to go more than twice as fast to escape Earth's gravity. Not an easy jump. While gravitational interactions during the merger will change many stellar orbits, the chance of the Sun gaining that much extra speed is small. Simulations suggest that only a small fraction of stars are fully ejected into intergalactic space during major mergers. But small is not zero. Some stars will be thrown out. These stars become intergalactic wanderers, drifting in the darkness between galaxies. They would carry their planets with them. If those planets remain bound, now imagine what that would look like from Earth, if Earth were still around. The night sky would change in a dramatic way. Without the dense background of billions of stars in a galactic disk, the sky would grow darker. The Milky Way band would fade away. Only distant galaxies would remain, faint smudges of light scattered across blackness. It would be a lonely sky. You might wonder, if Earth were ejected, would it be cold and lifeless? Not necessarily. At least not immediately. Earth's warmth comes primarily from the sun, not from the galaxy. As long as the sun remains stable, Earth would still receive its light and heat, but over very long timescales, isolation would mean fewer nearby stellar encounters, fewer external influences. It would be like living in a quiet cabin far from any city lights, peaceful, but remote. Still, the more likely scenario is that the sun remains gravitationally bound to the newly formed galaxy. After the merger, it may move to a different region, perhaps farther from the center, but not entirely alone in intergalactic space. And here's something comforting. Even during a merger, direct close encounters between stars are rare. Space is simply too vast. If the sun were a marble, and nearby stars were marbles separated by thousands of kilometers, even during the merger, the chance of two marbles hitting is tiny. The most common outcome is orbital reshuffling, not violent expulsion. But there is another possibility to consider. Even if the sun remains in the merged galaxy, could a close stellar pass disturb the outer solar system? Yes, if a star passed within a few thousand astronomical units. Remember, 1 astronomical unit is the distance between Earth and the Sun. It could disturb distant icy bodies in the Oort cloud. The Oort cloud is a vast shell of icy objects that may extend up to 100,000 astronomical units from the Sun. That's about 2 light years. If Earth's orbit were the size of a coin, the Oort cloud would stretch for kilometers in every direction. A passing star could send some of those icy objects inward, creating increased comet activity in the inner solar system. But even that would unfold over long timescales. Nothing sudden, nothing explosive, just gradual changes. And there is one final perspective to hold gently in mind. By the time the galaxies are deeply merging, about 4 to 5 billion years from now, the Sun itself will be nearing the end of its stable life. It will begin expanding into a red giant, so the larger galactic reshaping may not be the biggest challenge for Earth. The Sun's evolution may matter far more. In the grand scale of things, the galaxy's collision is dramatic and beautiful. But for our planet, the most immediate long-term threat comes from our own star. So could Earth be ejected? Yes, in theory. Is it likely? Not very. More likely, the solar system will remain part of the new galaxy, drifting through a reshaped cosmic home. And if any life still exists to look up at the sky during that distant era, what they would see would be unlike anything we see tonight. A sky transformed, a neighboring galaxy no longer a faint blur, but something vast and overwhelming, filling the heavens. Right now, if you step outside on a very dark night, far from city lights, you can see a faint band of light stretching across the sky. That soft glow is the disk of the Milky Way seen from the inside. And if your eyes adjust long enough, and the sky is clear, you might notice a small hazy patch in the constellation Andromeda. That faint smudge is the Andromeda galaxy. Right now, it appears about 6 times wider than the full moon in the sky, but so dim that most of its true size is hard to see without long-exposure photography. It looks small, quiet, almost unimportant. But over the next few billion years, that view would slowly change. At first, the change would be subtle. Over thousands of years, Andromeda would grow just slightly larger over millions of years. Its structure would begin to sharpen. Its bright central core would become more noticeable. If you could watch time pass like flipping pages in a book, you would see it expanding outward in the sky. Imagine watching a distant ship slowly approach across a calm ocean. At first it is a tiny dot, then over time you begin to see its shape, then its details. That is what Andromeda would become. After perhaps 2 billion years from now, it would appear several times larger than it does today. Its spiral arms would become visible as faint arcs of light, stretching across the darkness. Eventually, as the galaxies near their first close pass, around 4 billion years in the future, Andromeda would dominate the sky, could stretch from one horizon to the other. If the full moon today is about half a degree wide in the sky, Andromeda during its closest approach might span tens of degrees. That's like comparing a coin held at arm's length to something as wide as your entire outstretched hand. The sky would not be empty between stars anymore. It would be filled with glowing structure. You might ask, would it be bright like daytime? No. Even though Andromeda contains hundreds of billions of stars, they are still very far away. The light would be brighter than what we see now, but not enough to turn night into day. Instead, it would be like a permanent, soft glow across large sections of the sky, more like a distant city skyline glowing on the horizon. Beautiful, steady, and vast. As the tidal distortion phase begins, long arcs of stars would stretch between the two galaxies. These tidal tails could appear as faint bridges of light. From Earth, you might see luminous streams sweeping across the sky, connecting regions that were once separate. And then comes the first close pass. During that time, Andromeda and the Milky Way would overlap visually. The sky might show two bright cores, each surrounded by swirling, distorted arms. It would look chaotic, but also magnificent. You might wonder, would constellations disappear? Yes, slowly. The familiar patterns we know, Orion, Ursa Major, Scorpius, depend on the relative positions of nearby stars. Over tens of thousands of years, those stars already shift slightly. But during a galactic merger, as stellar orbits are altered, the sky's patterns would gradually become unfamiliar. Over millions of years, entirely new constellations would form. If someone were keeping star charts during that era, each generation would notice slight differences. Not overnight, but over long spans, the sky would feel new. There is something deeply humbling about that. We often think of the night sky as fixed and eternal. The same stars our ancestors saw thousands of years ago still shine above us. But in the far future, even the background of the universe will look different. As the galaxies merge further, bright starburst regions would appear. Clusters of young blue stars, hot and luminous, would glow like cosmic jewels scattered across the sky. Some regions might shine more intensely for a few million years before fading again. The sky would become dynamic, alive, and yet still slow. No sudden flashes, no explosive storms across the entire sky, just gradual transformation. If Earth, or whatever remains of it, were still orbiting the Sun during this time, an observer might see two galactic cores spiraling around each other over hundreds of millions of years. Imagine two glowing whirlpools, slowly circling in the heavens, and eventually those two cores would draw closer and closer until they merge into one brighter central region. At that point, the sky would change again. The spiral shapes we recognize today would fade. The structure would become more rounded, more diffuse. The Milky Way band would no longer appear as a thin stripe across the sky. Instead, the merged galaxy might look more like a broad, glowing cloud surrounding us in many directions. It would feel less like living inside a flat disk, and more like living inside a vast, luminous sphere. But remember, all of this unfolds over billions of years. If you imagine a single human lifetime as one grain of sand, the entire merger would be like a beach stretching beyond sight. No one would experience it as a sudden event. It would be part of the background of existence, a sky slowly changing across epochs. And while that sky reshapes itself, deep at the centers of both galaxies, something even more powerful would be happening. Two supermassive black holes, each weighing millions or billions of times more than our sun, would begin their own slow approach. Hidden in the glare of starlight, drawing closer, preparing for a meeting that would ripple across space itself. At the very center of the Milky Way lies something invisible, but incredibly powerful. A supermassive black hole called Sagittarius A. It has a mass about 4 million times greater than our Sun. If the Sun were a small coin, Sagittarius A would weigh as much as a mountain made entirely of those coins stacked together. And at the center of the Andromeda galaxy lies another supermassive black hole. Andromeda's central black hole is even larger. Estimates suggest it may contain around 100 million times the mass of the Sun. That's 25 times heavier than Sagittarius A. If Sagittarius A were the size of a small car, Andromeda's black hole would be more like a large building in comparison. For billions of years, these two giants have remained far apart, each anchoring its own galaxy. But as the galaxies merge, so too will their centers slowly drift toward each other. At first, the process is indirect. As stars and gas clouds interact, gravitational forces shuffle energy around. The dense cores of both galaxies gradually sink toward the middle of the combined system. You might wonder, how does something so massive move at all? The answer lies in dynamical friction. As a massive object, like a supermassive black hole, moves through a sea of stars and dark matter, it creates a gravitational wake behind it. That wake pulls backward, draining a little energy from the black hole's motion. Over millions of years, this slow braking effect causes it to spiral inward. Imagine pushing a heavy object through thick sand. It doesn't stop immediately, but it gradually slows and sinks. The same thing happens here, but on a scale of hundreds of thousands of light years. Eventually, the two black holes will come close enough to form a bound pair. They will begin orbiting each other. At first, the distance between them may be thousands of light years. That's still far. If one light year were a single step, that would be thousands of steps apart. But compared to the size of their galaxies, it's close. Over time, their orbit will shrink. As they circle each other, they fling nearby stars away, like tiny pebbles caught in a spinning sling. Each time a star passes near the pair, it can gain energy and be thrown outward. This removes energy from the black hole's orbit, bringing them closer together, slowly, patiently. The dance tightens. You might picture two figure skaters holding hands and spinning. As they pull their arms inward, they spin faster. The same principle applies here. As the black holes draw nearer, their orbital speed increases. What would this look like from afar? Not much at first. Black holes themselves do not glow, but gas falling into them can heat up and shine brightly. During the merger, large amounts of gas may funnel toward the center. This could create a quasar-like phase, where the central region shines with enormous energy. Quasars are among the brightest objects in the universe. A single quasar can outshine an entire galaxy. If the merged Milky Way Andromeda system entered such a phase, its core could blaze with light, but this would depend on how much gas remains available. You might ask, would this be dangerous for planets like Earth? Distance matters greatly. The center of our galaxy is about 26,000 light years away. Even if the black holes merge and release energy, that distance provides significant safety. It's like watching a massive fireworks display from across an ocean. Spectacular, but not directly harmful. Still, the final stages of the black hole dance are extraordinary. As their orbit shrinks to less than a single light year, about 6 trillion miles, which is still hundreds of times wider than our entire solar system, a new effect begins to dominate: gravitational waves. These are ripples in the fabric of space itself. When massive objects accelerate, they disturb space-time, sending waves outward at the speed of light. We have already detected gravitational waves from smaller black hole mergers using observatories like LIGO, but those involved black holes may be tens of times the mass of the Sun. The merger of supermassive black holes would release waves far more powerful as the two giants spiral closer, perhaps separated by less than the width of our solar system. They will circle each other in shorter and shorter times. What once took millions of years per orbit could shrink to years, then months, then days. In the final moments, they will be moving at speeds close to the speed of light. Imagine two mountains spinning around each other faster and faster, compressing the very space around them, and then, finally, they merge. In less than a second, two become one. The energy released in gravitational waves during that final moment could briefly outshine all the stars in the observable universe combined, though much of that energy would pass quietly through space as ripples we cannot see. From Earth's perspective, if observers still existed billions of years from now, they might detect those waves as subtle distortions measured by advanced instruments. But visually, the sky would remain calm. No explosion visible across the heavens, just a quiet shift in the center of the merged galaxy. One larger black hole now resides there, perhaps over 100 million times the mass of the Sun. The dance complete. Yet even that enormous merger is not the end of the story, because the ripples from such a union travel outward across the universe, carrying a message that gravity can shake space itself. And somewhere, perhaps in distant galaxies, other civilizations might one day detect that signal, just as we have begun detecting smaller ones today. As the two supermassive black holes spiral closer, their motion becomes faster and more intense. For millions of years, they circle each other slowly. The distance between them shrinks bit by bit. Stars are flung outward. Gas is stirred and heated. The core of the merging galaxy grows denser. Then the pace changes. When the two black holes are separated by less than a light year, about 6 trillion miles, or nearly 60,000 times the distance between Earth and the Sun, gravitational waves begin carrying away energy more efficiently. You might remember that gravitational waves are ripples in space itself. Imagine dropping a stone into a still pond. Ripples spread outward in circles. Now imagine that the pond is not water, but space-time, and instead of a stone, you drop two objects, each weighing millions or even hundreds of millions of suns. The ripples would be extraordinary. As the orbit tightens, the black holes begin circling each other faster and faster. What once took millions of years per orbit may shrink to thousands of years, then hundreds, then just years. In the final stage, they could orbit each other in hours, and their speed becomes astonishing. Close to the end, each black hole may move at a significant fraction of the speed of light. Light travels about 300,000 kilometers per second, fast enough to circle Earth 7 times in a single second. The black holes might reach speeds of tens of thousands of kilometers per second as they whirl around each other. It is like two mountains spinning around one another faster than any object you've ever seen. You might ask, do black holes actually touch? In a way, yes. When they get close enough, their event horizons, the invisible boundaries beyond which nothing can escape, merge into one larger horizon. But the final moment happens quickly. In less than a second, two enormous wells in space-time become one. The energy released during that final merger is difficult to imagine. For a brief instant, the power carried away as gravitational waves may exceed the combined light output of every star in the observable universe. That sounds overwhelming, but here's something calming. Almost all of that energy is released not as light, not as radiation that could harm planets, but as gravitational waves. These waves pass through matter almost undisturbed. They stretch and squeeze space by tiny amounts. Even when we detected gravitational waves here on Earth using LIGO, the change in length they measured was smaller than the width of a proton, far smaller than the size of an atom. So even though the energy involved is enormous, its effects at large distances are subtle. If observers were living 26,000 light-years away, roughly our Sun's current distance from the galactic center, they might not feel anything directly. Advanced instruments could detect the ripple passing through space, but no shock wave would sweep across the sky. There is another interesting possibility. When two black holes merge, they do not always remain perfectly still afterward. If the gravitational waves are emitted more strongly in one direction than another, the newly formed black hole can receive a kick. This recoil can send it moving through space at thousands of kilometers per second. If that happened in the merged Milky Way Andromeda galaxy, the central black hole might shift slightly from its original position. It could wobble before settling back into the center. In extreme cases in other galaxies, recoiling black holes have been ejected entirely from their host galaxies. But for something as massive as the combined Milky Way Andromeda core, complete ejection would be unlikely. More likely, the new supermassive black hole would remain near the center, now even larger than before. You might wonder, what would its mass be? If Sagittarius A has about 4 million solar masses, and Andromeda's central black hole has around 100 million solar masses, the merged black hole might end up with slightly less than their total combined mass, because some mass is converted into energy and carried away by gravitational waves. Still, it could weigh over 100 million times the mass of the Sun. If the Sun were the size of a small coin, this black hole would weigh as much as a mountain, made of those coins, stacked high into the sky. And yet, despite its mass, it would still occupy a relatively small region of space compared to the entire galaxy. The event horizon of such a black hole might be a few 100 million kilometers across, perhaps comparable to the size of Earth's orbit around the Sun. That sounds huge, but compared to a galaxy spanning hundreds of thousands of light years, it's tiny. It is like placing a single grain of sand at the center of a vast stadium, and still, it controls the motion of stars near the core. After the merger, the central region of the new galaxy may glow brightly for a time. Gas falling into the newly formed black hole could release intense radiation, creating an active galactic nucleus. From afar, the galaxy might shine more brightly than before, but eventually, as gas supplies thin out, the central brightness would fade. The black hole would remain quiet once again, waiting for new material to drift inward over billions of years. The dance would be complete. Two galaxies become one. Two black holes become one. Space itself ripples with the memory of their union. And somewhere in that vast system, stars continue orbiting. Planets continue circling their suns, and the long story of cosmic change moves forward, because even after such a dramatic merger, the universe does not pause. It continues, always reshaping, always evolving, and the newly formed galaxy, sometimes called Milkomeda, will begin its next chapter, no longer a spiral, but something different. When the two supermassive black holes finally merge, the most powerful signal they send out is not light. It is not an explosion in the usual sense. It is a ripple in space itself. Gravitational waves are difficult to picture because we are used to thinking of space as empty and still. But space is not just emptiness. It has structure. It can stretch. It can compress. Imagine drawing a grid on a rubber sheet. Now imagine pressing down hard in one place and then letting go. The sheet would ripple outward. Those ripples are similar, in concept, to gravitational waves. But instead of rubber, the sheet is space-time. When two massive objects, like the central black holes of the Milky Way and the Andromeda galaxy, spiral together and merge. They shake that sheet. The shaking travels outward at the speed of light. Light moves at about 300,000 kilometers per second. That's fast enough to circle Earth 7 times in 1 second. Gravitational waves move just as quickly. You might ask, how strong are these waves? At the source, they are unimaginably powerful. During the final fraction of a second of the merger, the energy released in gravitational waves can briefly exceed the total light output of all the stars in the observable universe combined. That sounds overwhelming. But energy spreads out. By the time those waves travel tens of thousands of light years to reach distant stars, or millions of light years to reach other galaxies, they weaken. By the time they pass through a planet like Earth, the stretching and squeezing effect is tiny. How tiny? When scientists detected gravitational waves here on Earth using LIGO, the change in distance they measured was smaller than the width of a single proton. A proton is so small that you could line up trillions of them across the width of a human hair. And yet, even though the stretching is small, the meaning is enormous. It means space itself carries information. When the Milky Way and Andromeda black holes merge billions of years from now, their gravitational waves will travel outward in all directions. If there are advanced civilizations in distant galaxies at that time, they might detect the signal. They would not see the merger directly, unless they had powerful telescopes pointed at our region, but they could measure the ripple passing through their detectors. It would be like hearing a distant drumbeat across the ocean. The signal would tell them that 2 massive black holes have become one. In fact, by the time that merger happens, gravitational wave astronomy may be far more advanced than it is today. Right now, we detect waves from smaller black hole mergers. Objects may be tens of times the mass of the Sun. These events occur billions of light years away, and yet, we can still measure their ripples. A supermassive black hole merger would produce lower frequency waves, longer and slower. Detecting those requires different instruments. Perhaps giant space-based detectors stretching millions of kilometers apart. Future observatories, possibly successors to planned missions like LISA, could be designed to capture exactly those signals. You might wonder, could humans, if they still exist billions of years from now, detect their own galaxy's merger if humanity survives that long? A big question in itself. And if advanced technology continues to grow, then yes, they could measure the slow tightening orbit of the 2 black holes. They could watch the gravitational waves increase in frequency and strength over millions of years, like listening to a drumbeat that slowly speeds up. In the final days before merger, the rhythm would accelerate dramatically. Then, in a brief moment, silence. The signal would change to that of a single larger black hole, settling into stability. There is something deeply poetic about this. Even events hidden behind darkness, even objects that emit no light, leave a trace in the fabric of reality. Nothing massive moves without consequence, and gravitational waves do not stop at the edge of a galaxy. They continue outward. They travel across the universe for billions of years. Long after the merged galaxy has settled into its new shape, the ripples will still be moving outward, crossing empty space, passing through stars and planets, gently stretching and squeezing them by tiny amounts. If 1 light year were the length of a football field, those waves would cross millions upon millions of football fields before reaching the edge of our observable universe, and they would keep going. In a way, the merger of the Milky Way and Andromeda will not just reshape one region of space, it will briefly echo across the cosmos, a signal that 2 giant structures have become one. And after the waves pass, after the central black hole settles, after the bright starburst phase fades, the new galaxy will take on a different form. The familiar spiral arms we know today will likely disappear. The thin disk of the Milky Way will not survive in its current shape. Instead, Something rounder, more diffuse, and more ancient-looking will emerge. A new galaxy, born not from destruction, but from merging, and its shape will tell the story of what came before. After the long approach, the tidal stretching, the bursts of new stars, and the merging of the central black holes, the two galaxies will no longer exist as separate spirals. The Milky Way and the Andromeda galaxy will have blended into something new. Astronomers sometimes give this future galaxy a nickname, Milkomeda. It's a simple way of saying that two become one. But what will this new galaxy actually look like? To understand that, imagine what happens when you spin two flat disks of sand into each other. At first, each disk has a clear shape, but once they collide and mix, the neat flat structure breaks apart. The grains scatter in many directions. The final pile becomes rounder, thicker, less organized. Something similar happens in galaxy mergers. Spiral galaxies are thin and flat. Their stars mostly orbit in the same plane, like cars driving around a circular track. That organized motion is what creates the spiral arms. But during a merger, gravitational forces disturb those orbits. Stars get pulled in new directions. Their paths tilt and stretch. Instead of moving in neat, flat circles, they begin orbiting in many different angles. Over time, the combined system loses its thin disk shape, becomes more rounded, more like a giant glowing ball of stars than a flat spiral. Astronomers call this type of galaxy an elliptical galaxy. If the Milky Way today is like a spinning vinyl record, the merged galaxy will be more like a three-dimensional cloud, thick in every direction. How big will it be? Likely larger than either galaxy alone. If the Milky Way is about 100,000 light-years across, and Andromeda about 220,000 light-years across, the final galaxy could stretch over several 100,000 light-years in diameter. If 1 light-year were the length of a football field, the new galaxy would span hundreds of thousands of those fields laid end to end, far beyond the horizon in every direction. It will contain perhaps over 1 trillion stars combined. That's 1,000 billion. If each star were a grain of sand, you would need enough sand to cover entire coastlines. And yet, despite this enormous number of stars, the galaxy will look calmer than the merging phase. Why? Because most of the gas will have been used up during the starburst periods. Spiral galaxies are rich in gas and dust, the raw materials for new stars. But when two spirals merge, much of that gas gets compressed and turned into stars relatively quickly. Once the gas supply runs low, star formation slows down. Elliptical galaxies are often described as red and dead. That phrase doesn't mean they are lifeless, but that they form fewer new stars. The stars inside them tend to be older and redder. Blue stars are hot and young. They burn brightly, but live short lives. Red stars are cooler and longer lived. Over billions of years, as new star formation decreases, the galaxy's overall color shifts toward red, so Milkomeda may glow softly, dominated by older stars. You might wonder, will the sun still be around to see this? The timing is close. The first major galactic pass happens in about 4 billion years. The full merger may take another 1 to 2 billion years after that. Around 5 billion years from now, the sun will begin expanding into a red giant. So during the final formation of Milkomeda, the sun may already be changing dramatically. If the sun survives long enough in its later stages, it would orbit within this new elliptical galaxy, perhaps far from the center, perhaps in a quiet outer region. The sky from a planet in that era would look different. Instead of a bright band across the sky, the stars would appear more evenly spread in all directions. It would feel less like living inside a flat disk and more like being surrounded by a vast glowing sphere. Constellations would be unfamiliar. The overall structure of the sky would feel thicker, fuller, and the central region, where the merged supermassive black hole now sits, might appear as a brighter, denser core. But there is something important to remember. This transformation is not unique. When we look deep into the universe today, we see many elliptical galaxies. Some are far larger than anything in our local region. Many of them are believed to be the result of past mergers. In other words, what will happen to the Milky Way and Andromeda has already happened countless times elsewhere. Galaxies grow by merging. Small ones combine into larger ones. Structure builds over time. You might ask, is this the final shape? For our local region, likely yes. After the Milky Way and Andromeda merge, there are few other large galaxies nearby to collide with. The remaining smaller dwarf galaxies in our local group will eventually be absorbed as well. Over tens of billions of years, Milky may stand mostly alone, because the universe itself is expanding, and distant galaxies are drifting away from us, faster and faster. So, in the far future, observers inside Milky may see a lonely universe. Nearby galaxies will have moved beyond the visible horizon, carried away by cosmic expansion. The sky would contain mostly the stars of one massive elliptical galaxy, a quiet, enormous system born from two spirals that once danced toward each other across millions of light years. A reminder that in the universe, nothing stays fixed. Forms change, shapes evolve, and even something as vast as a galaxy can be remade, not through sudden destruction, but through slow and patient merging. When we picture the Milky Way today, we often imagine its graceful spiral arms, long curved lanes of stars and gas wrapping around the center. Like the arms of a cosmic pinwheel, the Andromeda galaxy has them too. These spiral arms are not solid structures. They are more like traffic patterns. Stars move in and out of them as they orbit the center, similar to how cars move through areas of slow traffic on a highway. The arm itself is a region where stars and gas bunch together slightly. It is a delicate structure, and during a merger, delicate structures do not remain untouched. As tidal forces stretch the galaxies, and as stars are pulled into new paths, the neat flat disk that supports spiral arms begins to lose its shape. You might ask, why can't the arms survive? The answer lies in order. Spiral arms require stars to move mostly in the same flat plane, orbiting in roughly circular paths around the center. When the merger disturbs those paths, tilting them, stretching them, throwing them into new angles, the flatness disappears. Imagine a neatly stacked deck of cards lying flat on a table. Now imagine lifting the table and shaking it gently from different directions. The cards begin sliding out of alignment. The flat, clean structure becomes messy. That is what happens to the spiral arms. Stars no longer move in coordinated, flat patterns. Their orbits become more random. Instead of circling like cars on a racetrack, they move in many different directions. Some angled upward, some downward, some elongated into stretched loops. Over time, the clear spiral pattern fades. It doesn't vanish instantly. During the first close pass, the arms may become stretched into long tidal tails. They might look dramatic and beautiful, like ribbons of light pulled outward across hundreds of thousands of light years. If one light year were the length of a football field, those tidal tails could stretch across thousands upon thousands of fields. But those stretched arms are unstable. As the galaxies swing back together for their final merger, the repeated gravitational interactions scramble the orderly motion even more. By the time the merger is complete, the flat disk structure is gone. And without that flat disk, spiral arms cannot exist. The final galaxy, sometimes called Milky, will likely be elliptical in shape. Instead of thin and flat, it will be thick and rounded. You might wonder, does that mean the galaxy becomes chaotic? Interestingly, no. While the spiral arms disappear, the new galaxy settles into a different kind of stability. Stars orbit the center in many different directions, but the overall system becomes balanced. It is less organized in one sense, no flat disk, but still stable in another. It's like replacing a spinning vinyl record with a softly glowing ball of fireflies drifting in all directions. There is no single plane, but there is still gravity holding everything together. Another important factor is gas. Spiral arms are rich in gas and dust, which help form new stars. During the merger, much of that gas is used up in intense bursts of star formation. When the gas supply runs low, there is less material to define spiral patterns. Elliptical galaxies often contain older stars and less gas. Without large amounts of fresh gas flowing into flat disks, spiral arms are unlikely to reform. You might ask, could the new galaxy ever become spiral again? In theory, if enough new gas were added in the right way, perhaps from another future merger, a disk could form again. But in our local region, after the Milky Way and Andromeda merge, there are no other large galaxies nearby to supply that much gas. Over billions of years, the universe's expansion will carry distant galaxies farther away. Milky may remain relatively isolated, so the spiral era will likely end with this merger. The familiar bright band we see across the sky today, the Milky Way's disk, will fade into a different structure. If observers still exist on a planet orbiting a distant star in that future galaxy, the night sky would not show a thin stripe of stars across one direction. Instead, stars would appear more evenly distributed around them. It would feel like being inside a giant, softly glowing sphere. There is something bittersweet about that. Spiral galaxies are often seen as some of the most beautiful structures in the universe. Their arms curve gracefully, forming patterns that feel almost artistic. But beauty in the universe is not fixed. It evolves. The spiral arms of both galaxies are not permanent features. They are temporary arrangements of motion. For billions of years, they have held their shape. But gravity, given enough time, reshapes everything. You might find it comforting that this transformation is slow. If one human lifetime were a single second, the entire fading of the spiral arms would take longer than the age of all recorded history, multiplied millions of times over. No sudden collapse, no instant disappearance, just a gradual blending. Arms stretching, patterns softening, orbits tilting, until what was once a pair of flat, spinning disks becomes a single rounded galaxy filled with older stars. The spiral arms will not be destroyed in a fiery explosion. They will simply dissolve into a new form. And as they do, the gas and dust that once defined them will be scattered and reshaped, forming the building blocks of the next generation of stars. Because even as structure fades, new structure begins to emerge. When two spiral galaxies merge, stars mostly pass by one another in wide, graceful arcs. But gas and dust behave differently. Gas is not like stars. It can collide, it can compress, it can heat up and cool down. And during a merger, gas becomes one of the most important ingredients in shaping what comes next. Right now, the Milky Way contains vast clouds of hydrogen gas spread across its disk. Some of these clouds are hundreds of light years wide. If one light year were the length of a football field, a single giant gas cloud could stretch across hundreds of those fields placed side by side. The Andromeda galaxy contains similar clouds. During the tidal distortion phase and the first close pass, many of these clouds will collide directly. When gas clouds collide, they do not bounce apart like solid objects. They merge, compress, and slow down. The collision converts motion into heat. Shock waves travel through the gas, squeezing it into denser clumps. You might imagine two large weather systems meeting in Earth's atmosphere. When warm and cold air collide, storms form. In space, when gas clouds collide, star formation ignites. This is why mergers often create starburst periods, intense phases of rapid star birth. But that is only part of the story. Gas does not simply disappear after forming new stars. It moves. As gravity reshapes the merging galaxies, gas flows inward toward the center. Some of it funnels down toward the central black hole, feeding it. Some of it gets flung outward into long tidal tails, stretching across hundreds of thousands of light years. The distribution becomes chaotic at first. Imagine stirring cream into coffee. At first, clear patterns swirl through the liquid. But after enough stirring, the mixture becomes uniform. In a similar way, the neat lanes of gas that once traced spiral arms are disrupted. The flat disk structure that kept gas organized fades. Some gas sinks toward the center, thickening the core. Some gas is heated so strongly that it forms large, hot halos around the galaxy. Some gas escapes into intergalactic space. Over time, the merger redistributes this material into a new configuration. You might ask, what happens to the dust? Dust in galaxies consists of tiny solid particles, often made of carbon or silicate materials. Though small, dust plays a big role in cooling gas clouds, allowing them to collapse and form stars. During a merger, dust is mixed and scattered along with gas. Some of it gets incorporated into new stars and planetary systems. Some remain suspended in the interstellar medium, darkening certain regions by absorbing light. If you were observing the merging galaxies from afar, you might see dark lanes crossing bright star-forming regions, dust blocking the glow behind it. Over millions of years, however, as gas supplies are used up and redistributed, the overall amount of cool, dense gas decreases. Elliptical galaxies, the likely final form of the merger, tend to have much less cold gas than spiral galaxies. Without large reserves of cold gas, new star formation slows dramatically. You might picture it like a forest after a period of rapid growth. At first, seeds sprout everywhere, but once nutrients in the soil are used up and the canopy closes, fewer new trees grow. In Milky, much of the easily accessible gas may be consumed during the merger's active phases. What remains may be too hot or too diffuse to form new stars efficiently, and that changes the long-term future of the galaxy. Spiral galaxies often look blue in photographs because they contain many young, hot stars. These stars burn brightly, but live short lives, sometimes only a few million years. Elliptical galaxies, by contrast, tend to look redder. Their light is dominated by older, cooler stars, so the redistribution of gas and dust doesn't just change the galaxy's shape, it changes its color, it changes its future. There is also another subtle effect. As gas flows inward toward the center during the merger, it can build up pressure near the central supermassive black hole. If large amounts of gas fall in quickly, the black hole can become very active, producing powerful radiation and jets. These jets can push gas outward again, heating it and preventing it from cooling enough to form new stars. In that way, the black hole itself can regulate how much star formation continues. It becomes part of the galaxy's balance. You might wonder, is this violent? On human timescales, it would be impossible to witness the full transformation. But in cosmic terms, it is energetic, yet it is not chaotic in a sudden sense. It is a slow redistribution, gas drifting inward, dust mixing, new stars forming, old patterns dissolving. If you could watch it sped up like a time-lapse film, you would see clouds flowing along tidal streams, funneling into the core, glowing brightly, then fading as they are used up. Eventually, the merged galaxy settles, its gas more evenly spread, its dust mixed, its spiral arms gone, its star formation slowed, and what remains is a massive rounded galaxy, filled mostly with older stars, moving in many directions. But one important question remains. With all this reshaping, with starbursts and black hole activity and tidal forces, could life survive such a transformation? Would planets remain safe? Or would the merger create dangerous conditions across the galaxy? That gentle question leads us to consider the true risks and the surprising resilience of life in a changing cosmos. When people imagine galaxies colliding, it often feels like the ultimate disaster. Two vast star systems crashing together. Explosions, radiation, chaos everywhere. So a natural question rises gently in the mind. If life exists somewhere in the Milky Way, on Earth or on distant worlds, could it survive this merger? The calm answer is very likely yes. Let's begin with the biggest fear. Will stars crash into each other and wipe out planetary systems? As we've already explored, stars are incredibly far apart. If our sun were the size of a marble, the nearest star would be another marble thousands of kilometers away. Even when the Milky Way and the Andromeda galaxy pass through one another, most stars simply glide by at great distances. The chance of a direct stellar collision is extremely small, so planetary systems are not likely to be smashed apart. But what about radiation? During the merger, star formation increases. Many massive stars are born. Massive stars live fast and die young, often exploding as supernovae. Supernovae release intense radiation. Could that radiation harm life? Distance matters. A supernova would need to occur within perhaps 30 to 50 light years to pose a serious risk to a planet like Earth. 50 light years may sound large, but on a galactic scale, it is tiny. The Milky Way is about 100,000 light years across. So, while more supernovae may occur during a starburst phase, the odds of one happening dangerously close to a specific inhabited planet remain low. You might picture it like fireworks in a distant city. There may be many explosions, but unless one happens very close to you, you are safe. There is another fear people sometimes mention: gamma-ray bursts. These are extremely energetic flashes of radiation that can occur when massive stars collapse or when neutron stars merge. If one were pointed directly at a planet from nearby, it could strip away part of its atmosphere. But again, these events are rare and directional. The beam must be aimed precisely. Even during a galactic merger, the chance of a gamma-ray burst targeting a specific planet remains small. You might ask, what about the central black hole merger? When the supermassive black holes combine, they release enormous energy, mostly as gravitational waves. Those waves stretch and squeeze space by tiny amounts, but do not blast planets with harmful radiation. If gas falls rapidly into the merged black hole, it could produce bright radiation near the galactic center. But if a planet is tens of thousands of light years away, as Earth currently is, that distance provides strong protection. It's similar to watching a bright lighthouse from across a wide sea. The light is powerful, but distance keeps it safe. There is another subtle factor: stellar encounters. During the merger, stars may pass somewhat closer to one another than usual. A close pass could disturb the outer regions of a solar system, perhaps sending comets inward from distant reservoirs, like the Oort cloud. This could increase impacts over long periods, but even this is gradual, and life, as we know from Earth's history, can survive asteroid impacts, ice ages, and massive environmental changes. It adapts. You might find it surprising that galaxy mergers are not seen by astronomers as catastrophic for life on most planets. In fact, such mergers are common in the universe. When we look at distant galaxies, we often see systems in the middle of merging. If galaxy collisions automatically destroyed life everywhere, the universe would be a much harsher place. Instead, these events are part of normal cosmic evolution, and there is even a positive side. Mergers can trigger the formation of new stars and new planetary systems. The heavy elements needed for rocky planets, carbon, oxygen, iron, are created in stars and spread by supernovae. In a sense, galaxy mergers help recycle and redistribute the ingredients of life. You might wonder about Earth specifically. By the time the first close pass happens, about 4 billion years from now, Earth's own environment may already have changed dramatically due to the sun's increasing brightness. In about 1 billion years, the sun will be roughly 10% brighter than it is today. That may be enough to trigger significant changes in Earth's climate. In about 5 billion years, the sun will expand into a red giant. So the greatest threat to life on Earth may not be the galaxy merger at all. It may be our own star's natural evolution. That realization shifts the perspective. The galaxy collision feels enormous, but for a planet orbiting a stable star far from the center, the merger is not automatically a death sentence. It is a slow environmental change on a grand scale. And life, if it has billions of years to evolve, could adapt in ways we cannot yet imagine. Perhaps advanced civilizations might move their worlds, or build habitats around other stars, or even migrate between star systems. 4 billion years is an almost unimaginable amount of time for intelligence to grow and technology to advance. If humanity is only a few 100,000 years old as a species, then 4 billion years is 10,000 times longer than our entire existence so far. It's like comparing a single grain of sand to an entire mountain. So could life survive? Yes, in many places, it likely would. The merger is not a fiery apocalypse sweeping across the galaxy. It is a slow transformation, a reshaping of structure, a rearrangement of stars, and life tucked safely around distant suns may continue quietly, watching the sky slowly change over millions of years, because in the universe, even dramatic events unfold with patience. And survival often depends less on avoiding change and more on adapting to it. As vast and dramatic as the merger between the Milky Way and the Andromeda galaxy will be, there is something even closer to home that unfolds on a similar timescale. Our sun. Right now, the sun is about 4.6 billion years old. It is roughly halfway through its stable life. Stars like the sun shine by fusing hydrogen into helium in their cores. This process releases energy, the light and heat that make life on Earth possible. But hydrogen fuel does not last forever. In about 1 billion years, the sun will be about 10% brighter than it is today. That may not sound like much, but even a small increase in brightness can have large effects on a planet's climate. Imagine turning up a room heater by just a little. Over time, the room becomes noticeably warmer. On Earth, a 10% increase in solar brightness could raise global temperatures enough to trigger a runaway greenhouse effect. Oceans may begin to evaporate slowly. Water vapor, itself a greenhouse gas, would trap more heat, causing further warming. Long before the galaxy merger begins in earnest, Earth may already be changing dramatically. By about 3 to 4 billion years from now, around the time the galaxies begin their first close pass, the sun will be even brighter. Earth's surface could be too hot for liquid water. Life, if still present, may have retreated underground or to more protected environments. You might wonder, what happens next? Around 5 billion years from now, the sun will exhaust most of the hydrogen in its core. When that happens, its structure changes. The core contracts under gravity. The outer layers expand. The sun will become a red giant. Today, the sun's diameter is about 1.4 million kilometers, wide enough to fit more than 100 Earths across its face, side by side. But as a red giant, it may expand to hundreds of millions of kilometers in diameter. If the sun were the size of a basketball today, its red giant form would grow large enough to fill a small room. Its outer layers could reach as far as the current orbit of Mercury, possibly even Venus. Some models suggest Earth might be engulfed. Others suggest Earth could drift slightly outward as the sun loses mass and survive just outside the expanded envelope. But it would be scorched and unrecognizable. In any case, Earth as we know it would not remain habitable. So here is the quiet perspective. The first major encounter between the Milky Way and Andromeda is expected in about 4 billion years. The Sun's red giant phase begins around 5 billion years from now. These two events overlap in time. While galaxies stretch and tidal tails sweep across hundreds of thousands of light years, the Sun will be undergoing its own transformation. In some sense, for Earth, the Sun's evolution is the more immediate story. The galaxy merger is vast and beautiful, but the Sun's expansion directly affects our planet. You might ask, does the Sun's change interact with the galaxy merger? Not directly. The Sun's evolution is driven by processes inside its core, nuclear fusion, and gravity. The galaxy merger changes the Sun's orbit over long timescales, but it does not alter the physics inside the Sun itself. The two stories unfold side by side, one on the scale of millions of kilometers, the other on the scale of hundreds of thousands of light years, both governed by gravity. There is something almost poetic in that alignment. Around the time two great galaxies combine into one, our star reaches the end of its stable life. One structure dissolves into another. One star transforms into something new. After the red giant phase, the Sun will shed its outer layers, forming a planetary nebula, a glowing shell of gas expanding outward into space. The remaining core will become a white dwarf, about the size of Earth, but containing roughly half the Sun's mass. If the Sun today were the size of a basketball, the white dwarf would be like a small marble, but with enormous density. A teaspoon of white dwarf material would weigh as much as a large mountain on Earth. The white dwarf will no longer produce energy through fusion. It will slowly cool over billions of years. So by the time the merged galaxy settles into its elliptical shape, the Sun may already be a dim, cooling ember. If any planets remain in orbit, they would circle a faint white dwarf instead of a bright yellow star. You might find it humbling that while we focus on distant galactic events, our own star has a timeline just as dramatic. In about 1 billion years, Earth's climate may shift dramatically. In 4 billion years, the sky will be filled with the approaching Andromeda. In 5 billion years, the Sun will expand. In 6 to 7 billion years, it will shrink into a white dwarf. These are vast spans of time. If all of human history were compressed into 1 minute, then 5 billion years would be like stretching that minute into more than 80,000 years of continuous ticking. It is almost impossible to feel such timescales emotionally. But they remind us of something important. Nothing in the universe is static. Stars evolve, galaxies merge, structures transform, and the collision between the Milky Way and Andromeda is not an isolated event in time. It is part of a larger story, one that includes the life and death of our own Sun, a reminder that even as galaxies reshape the sky, the most personal changes may be happening much closer to home. When we speak about events 4 or 5 billion years in the future, a quiet and almost unbelievable question rises. Will anyone be here to see it? Right now, modern humans have existed for roughly 300,000 years. If you imagine Earth's 4.5 billion year history compressed into a single 24-hour day, humans appear only in the final few seconds before midnight. That is how young we are. The first close pass between the Milky Way and the Andromeda galaxy will happen in about 4 billion years. 4 billion years. If human history were one step, that time span would be a journey around the entire planet, many times over. So the honest answer is, we don't know. Human civilization as we recognize it is only a few thousand years old. Even agriculture is just around 10,000 years old. A blink compared to galactic timescales. It would be easy to assume that no civilization could last billions of years. But let's explore the possibility gently. Technology has grown rapidly in just the past few centuries. In about 100 years, we moved from the first powered flight to landing spacecraft on distant planets. That kind of acceleration is difficult to predict forward. If intelligent life survives its early challenges, war, climate change, resource limits, it may reach a point where it can manage energy on scales far beyond what we use today. There is a concept called the Kardashev scale, which measures civilizations by how much energy they can harness. A Type 1 civilization controls the energy of its planet. A Type 2 civilization controls the energy of its star. A Type 3 civilization controls the energy of its galaxy. Right now, humanity is not yet Type 1. We use only a tiny fraction of the sunlight reaching Earth. But 4 billion years is an almost unimaginable stretch of time for development. If a civilization could survive even 1 million years, which is already more than 3 times longer than our species has existed, it might become profoundly different from what we know today. Bodies may change, consciousness may merge with machines, civilizations may spread beyond a single planet. You might wonder, would humans need to leave Earth? Yes. Long before the galaxies merge, the sun will grow brighter. Within about 1 billion years, Earth may become too hot for complex life. If intelligent beings still exist, they would need to move, perhaps to Mars, or to moons of outer planets, or to artificial habitats. Eventually, when the sun becomes a red giant in about 5 billion years, any civilization would need to migrate to another star system entirely. That sounds extreme, but consider this. The nearest star system, Alpha Centauri, is about 4.3 light-years away. That is, roughly 40 trillion kilometers. If 1 kilometer were a single step, that distance would require walking around Earth many times over. Today, that distance feels unreachable. But over millions of years of technological growth, new methods of travel may become possible. Generation ships, artificial habitats, traveling slowly between stars, perhaps even technologies we cannot yet imagine. If intelligent life spreads to many star systems, then the galaxy merger becomes less of a threat and more of a spectacle. Imagine a future civilization observing Andromeda's growing disk across the sky. They might already inhabit thousands of star systems. They might have telescopes the size of small moons. They might study the merger in detail, predicting the path of every major cluster. They could even prepare for changes in stellar neighborhoods. You might ask, would advanced beings fear the merger? Probably not. As we've seen, galaxy collisions are not explosive disasters. They are slow reshaping events. Civilizations with the ability to move between stars would likely adapt easily. In fact, the merger might provide new opportunities. New stars forming, new planetary systems, new regions of space to explore. There is also the possibility that humanity or its descendants could merge with artificial intelligence. Minds might exist in digital form, stored in durable structures that can survive harsh environments. In that case, survival might not depend on a single planet at all. 4 billion years is long enough for evolution to take unexpected turns, but we must also consider humility. Most species that have ever lived on Earth are extinct. The universe does not guarantee survival. Intelligent life must choose stability, cooperation, and long-term thinking if it hopes to endure. So will humanity still exist? We cannot know, but the timescale allows for extraordinary transformation. If a civilization lasts long enough to witness galaxies merging, it would likely be profoundly different from us. It might not even call itself human. And yet, it could trace its origins back to a small blue planet, orbiting a middle-aged star. If such beings look up at the sky during the merger, they may not see danger. They may see history unfolding. They may understand that their own survival has carried them across billions of years of cosmic change, and they may feel something we feel even now, a quiet awe that they are part of something far larger than themselves. Because whether or not humanity endures, the galaxies will continue their slow dance. And if intelligence survives long enough, it may not only witness that dance, it may learn to shape its own place within it. If a civilization were to survive for billions of years, long enough to witness the merger of the Milky Way and the Andromeda galaxy, another quiet question begins to form. Would they simply watch? Or could they shape what happens? Right now, that idea feels far beyond us. We struggle to manage energy on a planetary scale. Redirecting the motion of stars sounds like science fiction. But let's explore it calmly. The merger itself is driven by gravity. Two galaxies, each containing hundreds of billions of stars and vast halos of dark matter, are falling toward each other under mutual attraction. To stop that fall, you would need to change the motion of objects weighing more than 1 trillion suns combined. That is an enormous amount of mass. If our sun weighs about 2 times 10 to the power of 30 kilograms, that's a 2 followed by 30 zeros. Then a galaxy containing hundreds of billions of stars weighs roughly 10 to the power of 11 times that. The numbers become almost too large to picture. So could a civilization realistically prevent the merger? Probably not in the simple sense of pushing the galaxies apart. The energy required would be far beyond anything we currently understand how to control. But perhaps the question is not about stopping the merger. Perhaps it is about adapting to it. On the Kardashev scale, a Type 2 civilization can harness the energy output of its star. A Type 3 civilization can harness the energy of an entire galaxy to capture a star's full energy. One idea often imagined is a Dyson sphere, a vast structure surrounding a star to collect its light. If our sun's total energy output is about 4 times 10 to the power of 26 watts, that's more energy every second than humanity uses in many years combined. A civilization that can capture that level of energy for many stars could, in principle, move stars. How would you move a star? You cannot push it like a rocket. But you could, in theory, use controlled fusion or directed energy to create asymmetric radiation, gently nudging it over long periods. Even a tiny push, applied steadily over millions of years, can alter an orbit. Imagine pushing a massive ship across a calm sea. One shove does little. But if you push continuously for years, the course slowly changes. If a civilization had billions of years and access to stellar-scale energy, they might be able to adjust the orbits of selected stars, perhaps moving their own star to a safer region of the galaxy. You might wonder, safer from what? From dense star-forming regions, from close stellar encounters, from areas where gravitational disturbances are strongest during the merger. Instead of resisting the galactic dance, they could position themselves within it. There is another idea sometimes discussed: stellar migration. Even without moving entire galaxies, an advanced civilization might choose to migrate from star to star. Over time, if the sun's future red giant phase threatens its home planet, they could relocate to a younger star elsewhere in the galaxy. Over billions of years, slow interstellar travel might become routine, not in the dramatic warp speed sense, but in the patient, generational sense. If one journey takes 10,000 years, that sounds long to us, but compared to a 4 billion year timeline, 10,000 years is a single breath. A civilization thinking on those scales might plan migrations carefully, moving between stable regions as the galaxy reshapes itself. Could they influence the black hole merger at the center? That seems far less likely. The masses involved, millions to hundreds of millions of suns, are extreme. The gravitational forces near those black holes are beyond any engineering we can currently imagine. But perhaps they would not need to interfere. As we have seen, the merger is not an explosive threat to most planetary systems. It is a reshaping, a redistribution. So the real engineering challenge may not be altering the galaxy. It may be ensuring survival through time, managing planetary climates, harvesting stellar energy, preserving knowledge, avoiding self-destruction. You might ask, Would a civilization even care about preventing the merger? From a cosmic perspective, mergers are natural. They build larger galaxies, they create new stars, they recycle matter. Perhaps a mature civilization would see the merger not as a disaster to avoid, but as a grand event to observe. They might build observatories across thousands of star systems, tracking the motion of Andromeda as it fills the sky. They might map the gravitational waves from the central black hole merger. With instruments spanning millions of kilometers, they might archive the changing constellations across millions of years. In that sense, engineering the outcome may not mean stopping it. It may mean mastering your place within it. There is also a humbling thought. Even a Type 3 civilization, one capable of harnessing the energy of an entire galaxy, would still be subject to larger cosmic forces. The expansion of the universe, the eventual fading of stars, the slow cooling of space itself. No engineering can stop the universe from evolving. It can only navigate within that evolution. So could advanced humans engineer the outcome of the Milky Way-Andromeda collision? Not likely in the sense of preventing it, but perhaps in the sense of choosing where and how to exist within it. If intelligence endures long enough, it may become less about resisting cosmic change and more about flowing with it, adapting, planning, thinking in millions and billions of years, and watching as two great spirals become one, not as helpless observers, but as participants in a much larger story. Because even in a universe shaped by gravity, there may be room for intention, not to stop the dance, but to decide how to move within it. When we imagine the future merger between the Milky Way and the Andromeda galaxy, it can feel like a rare, once-in-a-lifetime cosmic event. Two giant spirals colliding, a sky transformed, a new galaxy born. But here is the quiet truth. This has happened before, many times. When astronomers point powerful telescopes deep into space, they are also looking back in time. Light from distant galaxies takes millions or even billions of years to reach us. So when we observe galaxies that are hundreds of millions of light years away, we see them as they were long ago. And what do we see? We see galaxies in the middle of merging, twisted shapes, long tidal tails stretching outward, two bright cores spiraling toward each other. Some look like graceful spirals being pulled apart. Others look chaotic and tangled. Some already appear rounded and smooth, the likely final stage of past mergers. In fact, many of the large elliptical galaxies we observe today are believed to be the result of earlier collisions. If the Milky Way were the size of a large plate, some of these giant ellipticals would be like massive serving trays, formed from multiple mergers over billions of years. You might ask, how do we know they formed that way? Clues are written into their structure. Elliptical galaxies often contain stars moving in many different directions, rather than in a flat disk. That kind of motion suggests past disruption. They also tend to contain older stars and less cold gas, signs that intense star formation happened long ago and then slowed down. Sometimes astronomers find faint tidal streams around galaxies, thin arcs of stars wrapping around them like ghostly ribbons. These streams are leftovers from smaller galaxies that were absorbed. Even our own Milky Way shows signs of past mergers. The galaxy is not pristine. It has grown by swallowing smaller neighbors. For example, the Milky Way is currently interacting with the Sagittarius dwarf galaxy, a much smaller galaxy being gradually pulled apart and absorbed. Its stars form a faint stream that wraps around our galaxy. If one light year were a football field, that stream would stretch across tens of thousands of fields, arcing around the Milky Way like a loose thread. So the Milky Way itself is already a product of merging. The future collision with Andromeda is simply the largest chapter in that ongoing process. You might find it comforting that galaxy mergers are not rare disasters. They are part of how galaxies grow. In the early universe, mergers were even more common. Galaxies were smaller and closer together, Over time, gravity pulled them into larger and larger systems. It's a bit like droplets of water forming on a cold surface. Small droplets merge into larger ones. Then those larger droplets merge again, forming bigger pools. Galaxies behave in a similar way. Small ones combine into medium ones. Medium ones combine into large ones. Structure builds gradually. You might wonder, are there galaxies merging right now that look like our future? Yes. Astronomers have observed pairs of spiral galaxies that strongly resemble what the Milky Way and Andromeda may look like during their encounter. Two spirals, arms stretched, cores approaching, star formation lighting up the regions where gas clouds collide. In some cases, we see the final result, a smooth, elliptical galaxy with little trace of its former spiral arms. So in a sense, the Milky Way-Andromeda merger is not unique. It is part of a repeating pattern across cosmic time. There is something grounding in that realization. The universe is not chaotic without reason. It follows patterns. Gravity gathers matter. Matter forms stars. Stars form galaxies. Galaxies merge and grow. And over billions of years, larger structures emerge. Even galaxy clusters, groups of hundreds or thousands of galaxies, form through merging on even grander scales. If one galaxy is like a city, a cluster is like an entire continent of cities bound together, and clusters too interact. But here is an interesting twist. While mergers were common in the past, the universe is expanding, and that expansion is accelerating due to dark energy. This means that in the very distant future, galaxies beyond our local group will drift farther and farther away. Eventually, they will move so far that their light can no longer reach us. So while the Milky Way and Andromeda are destined to merge, many other galaxies are escaping beyond our cosmic horizon. If observers live in the far future inside the merged Milky galaxy, they may see a mostly empty universe beyond their local system. They might not even realize that other galaxies once filled the sky. That is how dynamic the cosmos is. What feels permanent today is temporary on longer timescales. The Milky Way has merged before, it will merge again. And after the Milky Way and Andromeda combine, the new galaxy will likely absorb smaller companions over time. The cycle continues. Stars form, stars die, galaxies collide, new galaxies emerge, and the story repeats, written in the slow language of gravity. So when we imagine the future collision, we are not imagining the end. We are imagining the next step in a process that has been unfolding for more than 13 billion years, a process that shaped the galaxy we call home, and one that continues quietly everywhere we look. When we talk about the future collision between the Milky Way and the Andromeda galaxy, it can sound like a rare and distant event. But in truth, merging is already happening right now. The Milky Way is not alone. It is surrounded by dozens of smaller galaxies, many of them called dwarf galaxies. These dwarfs are tiny compared to the Milky Way. Some contain only a few billion stars. That may sound large, but compared to the Milky Way's hundreds of billions, they are more like small towns orbiting a giant city, and gravity is slowly pulling them in. One of the most well-known examples is the Sagittarius dwarf spheroidal galaxy. This small galaxy is currently being stretched and torn apart as it orbits the Milky Way. Its stars form long streams that wrap around our galaxy like faint ribbons. If 1 light year were the length of a football field, those streams would stretch across tens of thousands of football fields, arcing through space in enormous loops. You might wonder, can we see these streams? Not with the naked eye. They are too faint. But with large telescopes and careful measurements of star motions, astronomers can map them. They see clusters of stars moving together in patterns that reveal their shared origin. It's like watching a flock of birds flying in formation across a much larger sky. Over millions and billions of years, these smaller galaxies lose their structure. Their stars become part of the Milky Way's halo. the outer region of stars and dark matter surrounding the main disk. In fact, much of the Milky Way's outer halo is likely built from past mergers with dwarf galaxies. You might ask, has this happened before? Yes. Our galaxy's history is written in its stars. Some stars in the Milky Way have slightly different chemical compositions or unusual orbits compared to others. These differences suggest they were born in other galaxies and later absorbed. It's like finding people in a city who speak a different language and carry different traditions. Evidence of migration long ago. Another example is the Large Magellanic Cloud and its companion, the Small Magellanic Cloud. These two dwarf galaxies are visible from the southern hemisphere as faint cloudy patches in the sky. They orbit the Milky Way and are gradually being influenced by its gravity. The Large Magellanic Cloud alone contains billions of stars. If the Milky Way were the size of a large city, the Large Magellanic Cloud would be like a neighboring town being slowly pulled into the metropolitan area. Some studies suggest that the Large Magellanic Cloud itself may eventually merge with the Milky Way before Andromeda does. So by the time the Andromeda collision begins, the Milky Way may already be slightly larger due to these smaller mergers. You might wonder, do these smaller mergers cause dramatic changes? Usually not on a grand scale. Because the dwarf galaxies are much smaller, their absorption does not destroy the Milky Way's overall structure. Instead, they gently add stars and dark matter to the halo. It's more like adding ingredients to a large pot of soup. The flavor changes subtly, but the shape of the pot remains the same. However, over billions of years, many such small mergers can build up significant mass. This process is called hierarchical growth. Small systems combine to form larger ones. Those larger systems combine again, and so on. In fact, the Milky Way likely formed from many smaller proto-galaxies merging together in the early universe. What we see today as a single grand spiral may once have been a cluster of smaller star systems gradually pulled into one. You might ask, is Andromeda also absorbing smaller galaxies? Yes, Andromeda has its own collection of dwarf companions. It also shows tidal streams and evidence of past mergers. So when the Milky Way and Andromeda finally meet, they will not be untouched spirals. They will already be complex systems shaped by billions of years of smaller interactions. There is something steady about this. The galaxy merger is not a sudden interruption of calm. It is the next step in a process that has been ongoing for billions of years. Even now, as you sit here listening, the Milky Way is quietly reshaping itself by absorbing smaller neighbors. Stars from those dwarfs are drifting into new orbits. Dark matter halos are blending. The galaxy you see tonight is not the same as it was a billion years ago, and it will not be the same a billion years from now. The Andromeda collision is simply the largest chapter in a long history of merging, a story that began when the universe was young, a story that continues slowly and patiently, because in the cosmos, growth often happens not in sudden leaps, but in gradual gathering. Small into medium, medium into large, until two great spirals, each built from countless past mergers, finally come together themselves. And even then, the merging will not end. The new galaxy will continue absorbing what remains nearby, quietly, relentlessly, shaped by gravity's steady hand. When we step back from the details, the tidal tails, the black hole merger, the reshaped orbits, a larger pattern begins to appear. The future collision between the Milky Way and the Andromeda galaxy is not an accident. It is part of how the universe grows. In the very early universe, shortly after the Big Bang, matter was spread out almost evenly. Over time, tiny variations in density, small regions with slightly more matter than their surroundings, began pulling in more material through gravity. It's like placing a slightly heavier pebble in a calm pond. Water slowly gathers around it. The heavier it becomes, the stronger its pull. In space, those denser regions grew into clouds of gas and dark matter. Those clouds formed the first stars. Stars grouped into small galaxies, and small galaxies merged into larger ones. If one small galaxy is like a village, merging with another village creates a town. Towns merge into cities, cities into vast metropolitan regions, that is, cosmic evolution. The Milky Way itself was built from many smaller galaxies merging long ago, and Andromeda likely followed a similar path. So when the two meet in 4 or 5 billion years, it is simply the next stage in that pattern. You might wonder, does the universe always grow like this? In many ways, yes, at least on smaller scales. Gravity pulls matter together locally. But on the largest scales, something else is happening. The universe is expanding, and not just expanding, accelerating in its expansion due to something we call dark energy. Imagine dots drawn on a balloon. As you inflate the balloon, the dots move away from each other. The farther apart they are, the faster they separate. That's similar to what happens with galaxies across vast distances. So here is the interesting balance. Locally, gravity wins. The Milky Way and Andromeda are close enough that their mutual gravity overcomes cosmic expansion. They are falling toward each other. But galaxies beyond our local group are moving away from us faster and faster. In billions of years, those distant galaxies will be so far away that their light may never reach us again. If 1 light year were the length of a football field, some galaxies are already billions of football fields away and drifting farther every second. So while galaxies merge locally, the universe as a whole becomes emptier. It's a quiet contrast. On small scales, gathering. On large scales, spreading. The Milky Way-Andromeda merger shows us that structure in the universe is not fixed. Galaxies are not permanent shapes frozen in time. They are dynamic. They grow, they reshape, they evolve. You might ask, is there an end point to this process? Eventually, yes. As expansion continues, fewer and fewer galaxies will be able to merge because they will be too far apart. Local groups of galaxies will merge into single large systems, but beyond those groups, the universe will thin out. In the far future, tens of billions of years from now, Milky may be mostly alone in an expanding sea of darkness. Observers inside it may see only their own galaxy's stars. They may not even realize that the universe once contained trillions of galaxies. There is something profound in that idea. We live at a time when we can see distant galaxies, some billions of light years away. We can observe cosmic background radiation, the faint glow from the early universe. But future civilizations might not have access to that view. The universe will have expanded too much. The evidence will have faded beyond their horizon. So, in a way, we are living in a special era. One where we can see both the past and the large-scale structure of the cosmos. The Andromeda collision reminds us that even galaxies, objects spanning hundreds of thousands of light years and containing hundreds of billions of stars, are temporary forms. They are chapters in a longer story. Stars form inside galaxies. Planets form around stars. Life may form on some planets, and over billions of years, the galaxies themselves change. If Earth's entire history were a single day, galaxies merging would be like continents drifting over ours. Slow, patient, inevitable. And this process is not violent chaos. It is structured, predictable, governed by gravity. There is comfort in that predictability. The Milky Way and Andromeda are not racing randomly through space. Their paths follow clear physical laws. We can calculate their motion. We can simulate their future. The universe is vast, but it is not arbitrary. And when the two galaxies finally merge into one, they will not break the rules of nature. They will follow them. They will continue the same process that built the galaxies we see in the distant sky. Cosmic evolution is not about endings, it is about transformation, small into large, order into new order, patterns dissolving and reforming. The Andromeda collision is simply one more step in that endless unfolding, a reminder that nothing stays the same, but everything changes according to the same quiet laws. Gravity gathers, expansion separates, and between those forces, the universe shapes itself again and again. When we imagine the future meeting of the Milky Way and the Andromeda galaxy, it can feel like the climax of a cosmic story. Two giant spirals drifting toward one another, tidal arms stretching across hundreds of thousands of light years, starbursts igniting, black holes merging, a new galaxy taking shape. It sounds like an ending, but it isn't. It is simply a transition. The universe has been changing for about 13.8 billion years. That's 13.8 billion trips around the sun, if each trip were 1 year, a number so large that if you tried to count to it, one number per second, it would take you more than 400 years without stopping. And during all that time, galaxies have been forming, merging, reshaping. The Milky Way itself was not always a grand spiral. It was built from smaller systems that collided long ago. The atoms in your body were forged in stars that lived and died before our sun was even born. In that sense, the Andromeda collision is not the end of something beautiful. It is the continuation of a pattern that made us possible. You might ask, why does it feel so dramatic then? Because we think in human timescales. We measure change in years, decades, centuries. But the universe measures change in millions and billions of years. If one human lifetime were a single grain of sand, the full galactic merger would be like an entire desert, too vast to experience directly, yet steady. The galaxies are not rushing, they are not angry. They are following gravity. Gravity has no urgency. It pulls patiently. Over 4 billion years, Andromeda will approach. Over another billion or two, the merger will complete. Over tens of billions more, the new galaxy will settle and evolve. And even that is not final. Stars inside the merged galaxy will continue living and dying. Some will explode as supernovae, some will fade into white dwarfs. Massive stars may collapse into black holes. Stellar remnants will drift slowly through the galaxy's halo. In the far future, trillions of years from now, most stars will have burned out. The brightest eras of star formation will be long past. The universe will grow darker, colder, but even then, it will not be static. White dwarfs will cool. Black holes will slowly evaporate over unimaginable timescales, through a process called Hawking radiation. If 1 second were stretched to represent 1,000,000 years, the evaporation of a supermassive black hole would still take longer than the age of the universe many times over. The universe changes slowly, but relentlessly. That may be the most important realization. Nothing is permanent, not planets, not stars, not galaxies, not even the grand spirals we admire tonight. And yet, there is no sudden collapse in this story, no dramatic final explosion when Andromeda arrives. There is stretching, mixing, reforming. If you could stand on a distant planet billions of years from now and watch the merger unfold over millions of years, you would not feel panic. You would feel awe. The sky would shift slowly. Familiar constellations would fade. A new structure would emerge. Life, if present, would adapt or move. The universe would continue. There is something strangely comforting in that. The Andromeda collision reminds us that we are part of a much larger rhythm. We often think of the cosmos as fragile, but it is resilient in its own way. Structures dissolve, but new ones form. Spiral arms fade, but elliptical galaxies glow. Stars die, but their atoms become part of new stars, new planets, new possibilities. The terrifying realization is not that everything ends, it is that everything changes. and it keeps changing. No matter what we do, the universe does not pause. It does not hold on to any shape forever. It flows like a slow river of gravity and light. Tonight, when you look at that faint blur of Andromeda in the sky, you are seeing a future partner of our galaxy, a system containing perhaps 1 trillion stars, each with its own planets, its own stories. Between us, 2.5 million light-years of space, shrinking slowly at about 110 kilometers per second. That speed sounds fast, faster than any airplane, faster than any rocket we have built. In 1 second, Andromeda moves closer by a distance similar to driving across a large city. But compared to billions of years, it is gentle. It is patient. The collision will not happen in our lifetime, not in the lifetime of our species, not even before the sun itself changes form. It belongs to deep time, and deep time moves differently. When we zoom out far enough, the Andromeda merger is not a catastrophe. It is a chapter. One more merging in a universe built by merging. One more transformation in a cosmos defined by change. And perhaps that is the ultimate perspective. We live inside a galaxy that is temporary, orbiting a star that is temporary, on a planet that is temporary. Yet in this brief window, this tiny slice of cosmic time, we are able to understand the future of galaxies, to measure their motion, to predict their dance. That alone is extraordinary, because while galaxies drift and merge and reshape themselves across billions of years, for a short moment, consciousness has arisen within one of them, and it can look up, and it can know